Thank you very much. Evening everybody. Welcome to this introduction to sacred geometry. It's subtitled From the Dot to Hyperspace, No Previous Experience Necessary, and that's genuinely what we'll do over the next, like I say, it takes about an hour and a half, probably will be about an hour the first bit. It's always a bit random, can never tell quite how it's going to distribute itself. But you should get a fairly thorough introduction to the subject from this. The first half of it, I'm hoping I'm going to introduce these 5 basic shapes to you. They're called the Platonic forms, and those are the kind of aim, if you like, for the halfway point. In the second half, we're going to be talking about hypergeometry and various other shapes that are grown from the shapes we're going to learn about in the first half. It's a talk I've been doing for now 3 or 4 years, this one, but recently it's been sort of revamped and re-illustrated. We've got a load of models here that aren't very often seen, and some of the models I normally carry around I haven't got with me, so it's going to be a bit of a new thing, and I'm going to have to try and keep track of my notes, otherwise I'll miss out some of the important stuff. It's a great story. There's a bit of a density warning on this one. We're effectively going to do what's basically a whole term's work in about an hour and a half. You can just be thankful that they're going to give you a bit of a break in the middle, because some people do get to sit through the whole thing in 90 minutes, and it's but so even in doing it this way, you'll have a tendency, because there's a lot of stuff, maybe to want to wander off a bit, close your eyes and stuff. You don't need my permission for that. All of the information will go in anyway, even if you are nodding slightly. I know there's a couple of people here who will verify that that's the case. So the reason why we're interested in sacred geometry is because it's not just a matter of form. It's not just a matter of simple shapes. It's because it's the form of the world in which we live. Effectively, you can almost see the shape of the sub-ether in some of the shapes that we're looking at. Most importantly of all, the simple rules that we're going to look at today about growth and reflection and other things mean that right down to the tiniest scale and right up to the biggest scale, these are the geometries that count. So each of us is made up of billions of centres of vibrating energy. We now know that what we're calling particles are actually just little balls of energy. They're not hard at all, they're mostly space, and we're made up of billions of balls of energy functioning in a field that's made up of other lines and centres of force. So we and everything about us are made up of these little centres of energy. And the distribution of this energy is governed by the same geometries that define the cosmos. From the tiniest quantum event through all of biology to galaxies and the hearts of stars. The principles and forms examined in this presentation underlie absolutely everything. So it really doesn't matter what scale you're going to look at. You're going to see the kind of things we're going to show you today. There's not going to be any sums, there's only going to be images and models. That's not quite true, there's some tiny sums about halfway through, but they're totally non-threatening sums, and mostly it's to do with the shapes. The other thing that's important is that your biological system is already attuned to all of the shapes that I'm going to show you. This is another thing that I do occasionally, is we do a sort of ceremonial introduction to geometry, which actually wires these shapes into your electromagnetic system. And we can show using kinesiology that this is the case, that when you look at some of these shapes, you're stronger than when you don't look at them. So your system is already familiar with all of this stuff. And as I hold some of the shapes up, not all of them are here, I've got more that I'll use in the second half. Some of them are going to sing to you more than others. And that's because inside you, inside the resonant library of your DNA, there are counter codes for these geometric shapes. Your body, your biological system is reaching out to these things and singing to them. They're basically like frequencies of frozen light made out of brass and paper. These ones I made myself. I started off with white bits of paper and I made the forms on the computer and coloured them in, and then made these shapes out of them. All the metal ones that I'm going to use are made in Bali. We tried to get them made all over the world, and it turned out that the people who did commission them, they live in Bali or spend a lot of their time there. And they finally found, having gone round trying to find people in America and people here, the people who were going to build it were living in a rice paddy just on the other side of the town from where they lived. So I made the cardboard ones, the other ones are made in Bali. Sacred geometry, what is it? The word geometry is easy. The word geometry is really the way number unfolds into space. We're going to be looking at how that happens visually today. but also you can hear it. Music is geometry for the ears. All music is to do with vibration, and so is all form. So the geometry bit of it is the way number unfolds into space, either as sound or resonance, or as visible artifacts, or indeed as vastly complex living systems where tons of simple geometry is simply stacked up on top of itself. The real problem I had with defining the name of the talk was what is meant by the word sacred. It's actually a difficult word because it's defined really differently in different places. In the end, though, I thought that one of the best meanings for sacred is effectively that which remains unchanged over time. You know, most of the information that we get changes a lot. So our science, our science is changes regularly. It's constantly updated. Science tells us that given things are true right now, and then it changes its mind tomorrow when it finds something else. And these aren't small errors, you know. Sometimes it's like in Shakespeare's time, Rosalind said, "This earth of ours is but 6,000 years old," because that's what they believed then. They thought the earth was created 4004 BC. There's still, unfortunately, a substantial part of the population that believes that now. Of course, science is suggesting that the earth's actually 4,500 million years old now, which is a bit different from 6,000 years, no matter how much you cook it up. The thing about this information is that it's older than our oldest texts. So even our Bible, even our holy texts, they get updated all the time. So if you look at the Old Testament, you'll see that it's a kind of mixing of several different versions. It's constantly being edited and updated. So you'll see Joseph being thrown down the well once, but he's rescued twice because somebody doesn't manage to remove some of the older stuff that they don't want in there. Now this information hasn't changed. This stuff was first written down 350 years or so before Christ by a Greek called Euclid. And although we've learned lots and lots more about the geometry, we've learned loads more about its applicability, about where we're likely to find it, the actual basic data that I'm giving you today is older than our oldest texts. So it's remained unchanged over time, and that's what I think is sacred. I think that's a good definition for sacred. It's also at the foundation of all natural design, at the heart of things. Another definition I found that I quite like is that which is found at the core. And your immune system, when it's not being screwed about with too much, is actually capable of dealing with invading systems that have never been seen on planet Earth before. And it can do that because all of those invading things will be geometrically based, and so are you. So your immune system can look at what's coming in and it can come up with a suitable countermeasure because the whole thing's geometric. So your actual natural system is built of all of this, foundation of natural design. Another thing that was pointed out to me is that most of the geometry can be done without any measurements, without a protractor, without any of that complicated nonsense you got taught in geometry at school. All you need is a pair of compasses and a straight edge. A ruler can be, but it doesn't need to have gradations on it. And I know there's several people in this room now that have started finding out what fun it is just playing with the compasses and the straight edge. All of the geometry that's coming up here has been done that way. None of it, we haven't cheated on any of it. The thing is, again, because it's at the foundation of your natural design, as soon as your body starts playing with it, even the most simple things, even this, two circles, one based on the edge of another, it's just doing that and looking at it. When you paint it on a piece of paper instead of looking at one that somebody else has done, it becomes fascinating. And very quickly you can get drawn into this stuff. There's lots of books out there now showing you how to do it. Although when I first was taught about this stuff, there were hardly any geometry books out there. There were no toys to play with. But we were told by our teachers that over time these things would become available. And I literally went from having no interest in geometry to being a complete geometry nut, more or less overnight, as a result of being exposed to this material. So it's all I've put it all, I've made it all nice and posh and put a lot of bells and whistles on it, but it's still fundamentally the stuff that turned me on. And of course the principles of this stuff have been used in all of our sacred sites. They're used in ancient barrows, they're used in stone circles, they're used in churches. Even the New World Order is quite clearly, absolutely obsessed with these particular forms. Washington DC is laid out on this design. It's a vesica piscis, it's got key items at various points on it, and they project into this a lot of the other geometries that we're going to be seeing. Now, they don't go around building a whole new capital city that way for no good reason. And once again, the people that are using the geometry for those purposes understand entirely how resonantly important all of this stuff is. So, in order to, before we get down to the sort of actual geometry itself, we're going to work our way out of hyperspace, if you like, down towards the dots, which is where geometry starts. And as I kind of go backwards like that, gives me a bit of a chance to explain some ideas to you that are going to be helpful a little bit later on. And this is done by a chap called Mick the Moon. He's the man that runs my website for me. He's also my resident scientist who tells me when I'm bullshitting, so I try not to bullshit. He tells me this is a slice through a 7th dimensional hypercube. And Mick knows about these things. And already you can presumably see something that is not staying very flat on the screen. You should be seeing in there lots of little cubes are trying to jump at you. And also there should be spheres that look like they're made up of probably about 7 cubes, because it's 7-pointed symmetry in there. And the thing is that this is actually one of the first concepts we like to look at. As well as being a hyperdimensional thing that's just bending out at you, it's also absolutely flat. It's got a kind of length and a height to it, but it's made out of light just twinkling on that piece of sheet there. So it's got no thickness at all. It's a proper plane in the real sense of the word. The actual sense, the actual original design, can you turn on to the next picture for me? This is the thing from which that came. Mick had made that an arty thing, and he bent it and warped it and coloured it. But this is the original plate from which it comes. It's called a Penrose design. It's a kind of fractal shape because all it is 3 different shapes of diamond used to make a really complicated shape. We've got the diamond in the middle of the 7-pointed star here, and then the diamonds that surround that, and then the little thin diamond. And those 3 shapes are then used again and again to make this complicated design. This is the thing that I stole as my logo, so wherever I am on the internet you see one of those but coloured in. Now, most people will again be looking at spheres and cubes that are kind of not flat, they're kind of coming out of the screen at you. Everybody see that? And most people will be finding it hard to see symmetry in it. You can see symmetry in here, but the rest of it will be a bit wild to most of you, not all of you. And the thing is that if you look at this central point, see the 7-pointed star, then see these 7, then those, and let your eyes just move out in rings, out and out and out, you'll actually see that the symmetry goes all the way around. So there's 7 of these, and 7 of the next things out. And again, because we're all bipedal, we've got even numbers of things, we tend to look for even symmetry. And so once we see one of these hyperdimensional shapes, or something that's only got 7 or 9 in it, it really starts confusing our systems. Also, it's not something you come across very often, because dividing 360 into 7 is really quite difficult. So straight away we've got a couple of planes, a couple of flat things that look really 3D. And all that's happening here is these things are kind of growing from self-similarity. We might say Spirit's got this idea for 3 shapes, and then it's sorting out what it can do with them. I quite like the idea of making 3 concrete moulds that are like this, and then trying to get a patio or a path that works like this. It'd be really grand to sit down with pins on that, wouldn't it? So that's this image is a plane. It's 2D 3-element construction, but interacting with your cognition, it becomes something a whole lot more complex. It becomes a masterpiece of complexity. It's just basically a bunch of black lines on a flat surface, but not to us, it's not. Can I have the next picture? The next one's called a Koch snowflake. It's a simpler idea of the same thing. This is a closer thing to a fractal. What I did here was I've got several pieces of coloured card, and I kicked off with a big pink triangle in the middle. And then I made some green triangles whose sides were half the length of the pink triangle, and some orange ones that were in half the size of the green. And the result of that is that we can fit 4 of the green triangles into the pink. We could put that one in there, this one in here, that one in there, and there'd be room for another green triangle in the middle. So we can fit 4 green triangles in the pink, 4 orange into the green, 4 yellow into the orange. They're really fascinating this close up. They're all pulsing and checky, and pink into the yellow. Now, This already is a really beautiful looking thing, but you can see how just the simplest of plane shapes, just a triangle, by reflecting on itself, is already getting the idea of growth and pattern and beauty. You can see movement in this thing. This one thankfully does look just flat. Now, one of the important things about this particular shape, you can't quite see it properly because the top part of it is missing. If you put a triangle round this shape, you could keep adding more of these things. If I had an infinitely sharp pair of scissors, I could keep adding smaller and smaller triangles to this, and they'd never step outside the original triangle that it's sitting in. And we can see that because I started with a pink triangle, and then I did the green ones, then I did the orange, then I did the yellow, and then I did the little pink. And if you look, the tip of this orange is in line with the tip of that pink, and the tip of this pink's in line with the tip of the orange. So effectively, we could continue to cut smaller and smaller triangles and stick them on the outside of this. Its surface area would be growing forever, effectively, without it ever going outside the boundaries within which it grows. Now, here in the third dimension, we've got this impression that stuff can only grow at the expense of something else. Actually, in the hyperdimensions where we naturally reside, that's not the case. Everything exists where everything else already is. If you were to look at us from the dimension in which we actually exist, all of our hearts, for example, put out electrical signals that reach tens of feet away from the body. Effectively, all of our electrical heart signatures, if you like, are interwoven here. If you were to look at that particular image of this room, you wouldn't be able to see thousands of individuals. All you'd see is this huge pulsing ball of our heart energies responding to each other. So, this geometric idea that you can grow without stepping on the feet of other things is important, because you can do that. The other thing about this, we have the next picture, is that if we use the same triangles, we can get it to grow inwards as well. You can put a green triangle in the middle of the pink and then an orange in the middle of the green, and one way and the other, it can grow inwards as well. You could keep carrying, if you had the infinitely sharp pair of scissors, you could keep cutting smaller and smaller triangles from the middle. That's basically a simple fractal form. It is simply taking the original shape and taking something half the size but the same shape, and then from that growing a complicated pattern. It's not had to do very much work at all. Now, these ideas, this idea of kind of constantly changing a shape, was first developed by a guy called, or maths was first developed by a guy called Leibniz a couple of hundred years ago. We have the next picture. And the result of that was these modern fractals. Now, these were in Leibniz's head 200 years ago. He kind of knew we'd be able to do this. But it wasn't until we developed computers that we had something that could do the thousands of millions of calculations necessary to produce an image like this. Now, effectively, there's lots and lots of different fractal designs like this, and all they are is a really simple equation where one side of the equation changes the other side. So if you say m equals m plus c, then whatever the c is, when you add it onto m, it changes the value of m, add c to it. And what the mathematicians do is they get the computer to apply colours to the numeric values that are generated as a result, and the computer just runs away with it. Wherever there's complex colour, like here, the calculation is actually running. Wherever it just goes into a plain colour like this, it's kind of, if you like, gone away and the calculation is not running. And the important thing about this is that all of these little trident bits are kind of like modelled on each other, and they're existing on lots and lots and lots of different scales. But what is happening here is, originally there had just been like a single dot of the original thought, if you like, and then it just flowers like a rush onto the screen. And all of the stuff that occurs later is modelled, all the bigger, larger stuff that comes later on is modelled on the smaller, earlier stuff. There's nothing new being done in these shapes. It's all down to the initial conditions. So Leibniz came up with the maths. The computers came up with the ability for us actually to be able to see it some 10 or 20 years ago, and you can now get computer programs that actually manipulate these. They'll run them for you so you can see them moving, you can zoom into them. There's one I used to use called Fractint, which is still out there. But if you look Fractal up on the internet, you'll probably be able to find some software programs that make these on your computer. and they're fascinating. You just watch them unfurling away from you forever, changing colour, always being slightly different from what they were before, never the same. Obviously, if this was symmetrical, it would be really boring. It's its lack of symmetry that's doing the novelty work for it. And now, in the 20th century, we can wrap that pattern around a cauliflower. This is a Romanesco cauliflower, and it's working on exactly the same principle. It's effectively every tiny, you can't see it too well, it's being broken up by the nature of the fabric. But when you can see it, every single tiny little bit of the cauliflower is actually an echo of the bigger bit of the cauliflower, which is all an echo of the whole cauliflower. Now that's actually true of all cauliflowers. It's just especially true of these Romanescos. I love them. They taste different as well. I don't know whether it's the geometry. Probably not. So we went from computers, then we could see the fractal on a 2D screen. Now we've got kind of like a 3D fractal wrapped around the cauliflower. And it sort of brings us to the difficulty of dimensions. We've already noticed that we were looking at some plane shapes earlier on that were tending to look to us like they were 3D. And that's because there's a basic theory, and I think it's right, that you can only see the dimension you're in from the dimension above. Okay? So the thing is, if you want to see, if we imagine a two-dimensional creature, okay, so a two-dimensional creature is going to be a bit like these pictures. It's going to have length and width, say, but it's not going to have any depth. It's, say, only going to be the thickness of light on the surface of water, say, just a photon thick. Even that's thickness, so technically it's 3D. But let's imagine, if you were to, say, walk up to a lake and pull your trouser leg up and stick your foot into the lake, if we imagine that there was a bunch of 2D light entities just living on the surface of the lake, they would become aware basically that something had opened up in them, that some of them had been hustled to one side. But they'd have absolutely no idea, because they're 2D entities, they'd have no idea of your foot going down to the mud at the bottom of the lake. They'd have no idea of your head reaching up to the heaven, or the sky, or the mud, or anything. All they'd know about is their own little flickering existence on the top of the water. So, a clearer image of that is, here we've got, what's happening here is we're imagining a sphere hitting a place called flatland. And as the sphere touches flatland, a little dot appears in amongst all these 2D critters who've got depth and width but no thickness, or width and height but no width and length but no height, no thickness. And then as the sphere falls into flatland, a bigger hole appears in the middle of these creatures, and then once the sphere's halfway through, they're getting really jostled aside, and then as the sphere disappears, it goes down eventually to a dot again. Now, again, the artist, being a three-dimensional entity, has imagined himself looking down on this plane. Can you see he's made it 3D for us? And so as a result, we're imagining that these creatures would be able to see a circle, but they wouldn't. Because they'd be living, all they'd see is a straight line going away. Wherever they were, they wouldn't even be able to see the circle. You know? So, other things that would confuse them is if we chuck something a little bit more complex through, like a pipe. To start with, you'd get a little dot where the pipe bowl hits, then a bigger circle, and then eventually other little 2D critters are going to get started jostling like away from the main course of the action. And what basically happens is then several different things occur, then a couple of things, and then only one again, and then it's all stopped. Now, the 2D critters again would have no idea at all about the shape of this pipe, and they'd have some difficulty probably associating these various bits of activity with a single entity coming down through them. Now, the point of all of this, of course, is that we've probably got similar blind spots living in the third dimension. In fact, we certainly have got similar blind spots. Just like the 2D characters cannot imagine somebody like us looming over them and being able to see all of their little world down there on, you know, whatever 2D surface it's on. There's things that we can't see from where we are. However, the important conclusion about the dimension idea is that if you have to be above the dimension you're in to see it, then we must be at least fourth dimensional entities. And that's put forward as the reason for why we have so much difficulty trying to keep flat things looking flat. Here's a really simple example. What it is it's a Necker cube. which basically is a cube that's got a square at the front and a square at the back. And you can make it look so that that's the case, but you can also make it look so that the square at the back is at the front. Has anybody seen any of the pictures that have got things like an old lady and a hag in the same picture? Because that's what we're talking about here. This would show it you geometrically, but unfortunately we'll have to do it with our heads instead. The thing is that when you're looking at the old lady and the hag, some people see first the hag and can't see the young lady. Some people first see the young lady and not the hag. Some people can see both, but you can only see one at a time. You can't see them both at once. Just like with this cube, if you could see it at all, you'd only be able to see one of them, and then you'd be able to see the other. Now, this takes us to one of the places where even simple geometry can start reflecting really important scientific ideas. Because one of the explanations currently for quantum reality, for the way that reality kind of stems from an interaction with consciousness, physicists have known this is the case, but they don't like it. One of the explanations they've come up with is that stuff emerges from the fundamental unconscious ground of being as it encounters consciousness, and then it folds itself back into the unconscious again. Now, there's a scientist called David Bohm who calls these two states the implicate and the explicate. He says the explicate is where we live, the stuff that's been explained and encountered by consciousness. The implicate order is where stuff resides until it encounters consciousness. Now, effectively, physics has known for some time that stuff kind of exists in a state of might-be-ness. Something might be going like this, all the different states it can be in, and then somebody sees it and it goes, I'm one of those. And at the same time that happens, there'll be another one over here going like this, and this one will go like that. Without anybody looking at it at all, it'll form a complementary part to this. Now, that they know for some reason happens when when consciousness encounters form. And these things show you. If you could see this, half of the audience, say we had a picture of the old hag and the pretty lady up there, half of the audience would probably be seeing the old hag, half of the audience would be seeing the pretty lady. So for half of you, the pretty lady would be in the explicate out here, and for the other half, the old hag would be. Which means that in this room, both of them would be in the field of consciousness, unless by some chance all of you were only seeing one form of the picture. Now all of this is your consciousness determining the difference between one thing and another. And the point is, once you've got the two pictures in your head, if you could see the two different cubes here, you could only slip between one and the other about 6 times a second. And you couldn't see them both at once. So effectively, you're pulling stuff out of the implicate order and putting it away again all the time in 6-second slices. So you're actually seeing it a bit like a video. And of course, in that one, because there's only kind of 2 faces to it, or like the pretty lady and the hag, there's every chance that the 2 possibilities are being witnessed by a room, especially with this many people in it. This is a much more complicated one. This is another hypercube. This is a thing called a tesseract, which I sometimes got a model of, but I haven't got this time. When you look at that, we should be able to see several cubes. Let's see if I can pick one out for you. It's very difficult when some of the design is missing. But you should be able to see, here we go, there's the front of a cube, the side of a cube, and the back of a cube there. And they're all kind of interrelated with each other. We've got a 3-dimensional model of this thing, and when the little man in Barney was asked to make it, he showed him this picture, put it on a table, and he looked at it, and then he went up to it and he went, like he was expecting to find something underneath the paper. And a little bit of him kind of went hyperdimensional at the moment that he did that. So, flatland representation of the tesseract, there we go. So, this one's slightly more complicated because here there's loads and loads of implicate orders and you're only going to be able to get one explicate out at a time. Because it's effectively the actual 3D form of this is 8 cubes stuck together, springing from a point that you can't see. Now that means that there's every chance that every single one of you is looking at a different part of this form. So some of it's coming into the explicate order where we are, some of it will be staying wholly implicate. But once again, your consciousness is It's not having so much difficulty as it would have if it could see the whole thing. There you go. Now, these are just simple black lines on a plain piece, on a piece of white paper. Nobody's trying to mess with your head specifically here. Once people do start trying to play with your 3D sense, you start getting yourself into all sorts of difficulty. This is a search I thoroughly recommend doing on the internet. Put in optical illusion street painting, and there's loads of these. This one, you can see that it's a road. It's one of those concrete section roads. Look, there's lines across here, the actual sections of the road itself. And what the guy's done is he's gone and he's painted on it, drawn on it with chalk, and got people to stand on it and make it look like it's what it isn't. Now there you go. Look at that. Imagine if you've got a head full of beer and came out of the pub and somebody had done that to the street. And the thing is, that's again, it's just really fooling you. If you see this on a high definition screen, it's really cunningly done. One of the important things is it has to be photographed from exactly the right angle in order for it to work. But there's everything. They've done giant frogs. One of my favourites is one with somebody feeding babies to goblins on a spoon. Really fantastic. But that's, I mean, this is a non-moving picture. This is what happens when people start playing with your three-dimensional sensors. And this is without sound and without movement and without special effects. Just imagine how much fooling is being done of you when you're looking at things that really are designed to mess with you. Now, this brings us to the kind of idea of holograms, 3D shapes that we can now make. Again, they stem from Leibniz's work, the work of the guy that came up with fractals. Everybody's probably seen little holograms on their credit cards and stuff. I normally carry around, but I haven't got it with me, a hologram of a bird. When you hold it up, what you can see is a picture of an owl in the middle of the picture, and it's about this big. And when you've got it with the sunlight behind your shoulder and you look at it, the owl is really sitting out from the glass. It's very, very 3D. Its eyes look ever so real. And the thing is that when you tilt the glass slightly one way, there's some sort of giant eagle on the side of it, and you turn it the other way and there's a fish-eating bird of some sort. So this one single glass plate carries three pictures that are very, very three-dimensional in them. And this came about, again, as a result of Leibniz's work with the maths. 200 years down the line, somebody came up with lasers, coherent light, and suddenly we can see another form of Leibniz's maths. The important thing about the fractal, about those holograms, is that if you break it, if you throw it on the ground, what you'll end up with is a load of pieces, each of which contain the whole image. So they'll still have the whole picture of the owl, the whole picture of the eagle, and the whole picture of whatever the sea-eating bird that hasn't yet been identified is. The only thing is that you'd lose a little bit of the depth and a little bit of the colour to go with the pictures, you see, and a little bit of the 3D, but nonetheless the whole thing would be there. And that's another important geometric idea. It's another idea that comes up again and again in this, is that the essence of the impossibly small contains the essence of the impossibly large. That basically every single bit of that hologram contains enough information to rebuild the whole system if you break it. And the same thing's true of what we're talking here. There's enough data in the smallest part of the cosmos, we reckon, to rebuild the entire system, because all it's doing is working on very, very basic, very simple principles and then reflecting upon those ideas. Now, the strange thing about the hologram is that if you look really hard at it, if you look at it especially with slightly blurred eyes and get the light on it so that it's just right, all you see is a bunch of curly green and black swirly patterns. That's all you see. There's actually none of that 3D imagery there at all. It's quite hard to do that with them, but fortunately that's a picture of this card. I've never managed to make what the card does work with the image on the screen, though I have tried it. Although it must be said, every time I see it, it looks different. It's a mass of yellow, green, blue, black. Most of the colours, most of the 7 or 8 colours are there. This is the first example of this thing I ever came across. It was in our loo for ages and I couldn't make it work. It is actually a 3D picture. And people's ways of dealing with them are all very different. I kind of relax my eyes and put it quite close and then move it away. What eventually happens is your eyes, your consciousness starts to notice something solidifying out of this shape. And what normally happens then, if you haven't done it before, is it will unsolidify, it'll retreat, your mind will go, "Ooh, what's that?" And you have to really relax into it. What this one produces is a set of coloured columns about this big. Swirly coloured columns, I think there's half a dozen of them, and they're pink and green and yellow on top, and they're kind of black underneath. And they kind of, you can almost look underneath them. Once you've got them working, I'll hand it round, and you can play with it in the interval and stuff. But the other thing that you notice when you do get it working is that the flat piece of card becomes slightly spherical. You see these columns springing out the top of it, and the card itself has just gone like it's part of the surface of a sphere. Because the spherical thing is also really crucial to the geometry. So I'll hand that round. You can give it a go. Be aware that that when you do get it to work and when you come back a little bit, you can get to feel a little bit queasy. The management hold no responsibility for the mess you might make. Here's a slightly simpler version. That one you can't tell what's going to come out at you, and it makes your mind, if you haven't done it before, quite difficult. This one, what this one does is it comes up with 3D versions of these images. So you will see exactly that, but it'll go 3D. There's a book here which is full of ones like the postcard, so you can't tell what's coming out of these at all. Now, what's going on there is that's what vesica piscis means. And although it's apparently a simple image, it relates geometry to the spiritual journey and the passage of birth. Basically that, for the geometrist, is representative of the birth canal. And we've also reached duality here. We've got a problem. We've already got before and after. We've got over here and over there. You've got good and bad. Duality's already occurred. This is the kind, when that fall that's talked about in the Bible is this. It is spirit reaching out into the third dimensional world, and on its first move towards becoming matter, to becoming the thing that we are. But right here, it's only made the first dimension. It's just made length. You know, it's just gone from one point to another, and all we've got is a straight line. The quickest way spirit can make a plane, something that's actually that these two worlds, these sort of flat critters could live in, is to go up to the top of that shape and come back down again. So what it's going to do, it's going to take 3 identical lines like that, and it's going to lean them against each other. Oh, it's not. First of all, we're going to see a cosmic vesica piscis. Okay. That's the thing called, the egg timer nebula, is what it is. And something appears to have happened here, and something appears to have happened over there, and the two colliding energy waves is where everything happens. Okay, where these two energy forces intermingle with each other, that's where you get something that looks like the Eye of Sauron. But the actual activity that's occurring there is occurring because of the interruffling of two sets of waves. And it's how, you can imagine, that's a very, very big vesica piscis. I was extremely pleased when I found that photograph. But I keep forgetting about it. 8,000 light years away, that is. But spirit, back to the simple story, if spirit wants to make a plane, the simplest plane it's going to be able to make is a triangle. And really, that's the kind of place where geometry starts and finishes. Lao Tzu said, 1 begat 2, 2 begat 3, and from 3 sprang 10,000 things. Everything springs from the triangle, effectively. We look at slightly more sophisticated geometries, but they're all based on that. The triangle, triunity, or 3 in 1. It's the preeminent symbol of divinity. It's the first plane we can get. In classical geometry, they talk about the good, the beautiful, and the true attached to the 3 points of the triangle. And when they're talking about the good is law, homogeneous and isomorphic are the 2 words that are used to describe that. And this was described as the first, as the seed, as foundation and unity, the base of absolutely everything. And it comes from the Greek roots to be stable and oneness. And the sphere's at the base of everything, as the monad is. Just like 5 times 1 equals 5 and 5 divided by 1 equals 5, this unity preserves the unity of everything that it encounters. The monad is all that there is. It's the container of everything, and it's a sphere whose centre is everywhere and whose boundary is nowhere. Okay? This is before anything's happened. We're quite interested in spheres. The reason why is because we look out at the world through spheres. The world that we live on is a sphere. If we look out into space, everything we see out there that's above a given size forms a sphere. The only jaggedy things are actually kind of smaller, below a given size. And also, all of the shapes that we're going to look at tonight are different ways of dividing a sphere into equal portions, and that's a particular interest to us, of course, because our cells do that. Our cells start off as spheres. The very first one, the egg, if you like, is visible apparently. It's big enough to be a visible cell, but they're all spherical to start with, and they all divide themselves using kind of similar techniques to the ones we're going to look at here. And the spheres actually go up and up. It's not just the Earth, not just our eyes and the Earth. When I first came across this image, I thought it was a picture of an eyeball because it's actually a very small gift, but when I looked at it, it turns out it's a picture of a thing that's called the Oort cloud, which is imagined to be a cloud of dust and comets that surrounds our solar system. Here's the Sun, here's the Earth. The Earth is 1 astronomical unit away from the Sun, i.e. third rock from the Sun. This is 10 astronomical units, this is 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5, so that's a long way away, big number. And outside our solar system, which kind of flies through the universe on a kind of like an inclined plate, is this huge cloud of dust and ice in the form of a sphere. And then I found out that there's also brown dwarfs out there. These are dying stars, dying suns. They've burnt all their hydrogen and are just burning helium or something. And they travel in clusters apparently, and they travel 300,000 light years above and below in a kind of spherical pattern. Again, round outside the Oort cloud. And then I became aware that actually when you look at galaxies and the way they're spread on a kind of normally a pretty flat plane, once again it's a spherical geometry that's defining the galaxy. And then the galaxies cluster, and there's spherical qualities to the superclusters and the clusters of galaxies as well. And then right out, as far as we can see, right out on the edge of the cosmos, there's these things called things like the Magellanic and the Centauri wall. And what these are described as is like a froth of bubbles. So even out there, there's spherical shapes, but these spheres are made out of walls of galaxies. Right the way around these empty spaces are walls of galaxies that might be tens of millions of light years thick, you know? But it's all spherical, the whole thing. And Leibniz had the idea right from the word go, right, all those years ago. This idea of unity in the sphere has been associated. Now, the geometric point of the form, when we take the sphere to the beginning of geometry, we take it right down to the dot. And we're actually at the same point here as we were with Leibniz's monad. In that we have to imagine that this thing can be, it's everything. It can be incredibly huge and everything, or incredibly small and everything. And I like to imagine that the sphere goes down and down and down and down until it just becomes this kind of uni sort of point, if you like. But in terms of geometrists, it's still what they call infinitesimal, infinitely dividable. Even if it's infinitely small, it's still infinitely dividable. So the geometrists were kind of getting to the idea of quantum physics. They kind of understood that a thing could be incredibly small and have infinite mass, or it could be incredibly big and have infinite volume. But from Spirit's point of view, what we need to imagine is that in that point it could grow as much as it likes, it could shrink as much as it likes, but it would always be just a circle. What we need to imagine for the action to start is we imagine Spirit sitting on its own, perfect, waiting to form. And what it does is it draws a circle around itself to remember where it is, to actually give it some sort of form. It maybe reaches out into the stuff around it, and there's, I don't know, a breathing out or a turning over or a bit of a vibration. Something happens to make something change, just like quantum physical theory suggests it might have done. And then we can imagine Spirit going, hey, I've got somewhere to go over there now. Okay, that's interesting. What happens if I go over there and do the same thing? So it moves over to the edge of the first circle that it's drawn and draws another circle around itself. And you get this shape, the cosmic yoni. Here it is in glass. This shape in the middle is where all geometry starts. It's also, of course, the shape of our eye, the shape of our nose, the shape of all of the holes in our body. It's a pretty important shape, so it's a very much a birthing thing, really. One of the new things that's happened to this geometry talk is I've redrawn it so that you can see all of the shapes we're going to talk about growing from this basic form. Because we can see that one of the easy ways of drawing geometry is to be able to play with that. As we see, if you do this again and again, you end up with one of these, the flower of life. And this one actually contains all of the geometry that we're going to look at. And you'll see that shape developing. So nothing exists without a centre around which it revolves. The centre is the source, and it's beyond understanding. It is unknowable, but like a seed, the centre will expand and fulfill itself as a circle, and then another circle. So it's gone from unity to duality, okay? We've gone from the monad to the dyad, two-ness. Nothing's changed. It's still oneness. This is oneness pretending to be two and taking itself seriously. And that's all that goes on from here. Loads and loads and loads of reflection. But it's still only oneness. It's really important to remember that. So the Greeks referred to this moment as audacity and anguish. Audacity for its brave separation from unity, and anguish because of its yearning to return to wholeness. And that's exactly the state we're in now. We're still yearning to return to wholeness. We're still living in a world where oneness is pretending to be many things and taking itself seriously. This shape, for some reason, is called the bladder of the fish. I don't know why. That's what vesica piscis means. And although it's apparently simple image, it relates geometry to the spiritual journey and the passage of birth. Basically, that for the geometrist is representative of the birth canal. And we've also reached duality here. We've got a problem. We've already got before and after. We've got over here and over there. You've got good and bad. Duality's already occurred. This is the kind, when that fall that's talked about in the Bible is this. It is spirit reaching out into the third dimensional world, and on its first move towards becoming matter, to becoming the thing that we are. But right here, it's only made the first dimension. It's just made length. You know, it's just gone from one point to another, and all we've got is a straight line. The quickest way spirit can make a plane, something that's actually that these two worlds, these sort of flat critters could live in, is to go up to the top of that shape and come back down again. So what it's going to do, it's going to take three identical lines like that, and it's going to lean them against each other. Oh, it's not. First of all, we're going to see a cosmic vesica piscis. Okay, that's the thing called the egg timer nebula. That's what it is, and something appears to have happened here, and something appears to have happened over there, and the two colliding energy waves is where everything happens. Okay, where these two energy forces intermingle with each other, that's where you get something that looks like the Eye of Sauron. But the actual activity that's occurring there is occurring because of the interruffling of two sets of waves. And it's how, you can imagine, that's a very, very big vesica piscis. I was extremely pleased when I found that photograph. But I keep forgetting about it. 8,000 light years away, that is. But spirit, back to the simple story, if spirit wants to make a plane, the simplest plane it's going to be able to make is a triangle. And really, that's the kind of place where geometry starts and finishes. Lao Tzu said, 1 begat 2, 2 begat 3, and from 3 sprang 10,000 things. Everything springs from the triangle, effectively. We look at slightly more sophisticated geometries, but they're all based on that. The triangle, triunity, or 3 in 1. It's the preeminent symbol of divinity. It's the first plane we can get. In classical geometry, they talk about the good, the beautiful, and the true attached to the 3 points of the triangle. And when they talk about, they're talking about the good is law, funnily enough, hasn't turned out too well, as we know. The beautiful is art, and the true is science. So law, art, and science are starting to build kind of other kind of knowledge on the geometry that they're discovering. So let's see where it's going to go next. There we go. What's happened, we can see that we've got a triangle formed just in the vesica piscis, just in here, just in there. If we want to form any other pictures, the way I do it is you draw a third circle on here, which is centred there, and then it's really easy to draw a hexagon. I like to make, I use these in the garden because I'm a landscape gardener. It's actually loads easier to make hexagons than it is to make squares or rectangles, because the sides of a hexagon are the same length as the radius here. And that makes it really easy, and that means that one of the first shapes that comes up when we're moving towards this flower of life, the first thing you get is a hexagon. You can't get to these shapes here are made of triangles, or squares, or and pentagons. So this is a bit of a sideline. This is more to do with the second half of the talk, but it just has to come in here, really. And that's where the square comes in. You can see that you can draw a perfect square. You've got a perfect hexagon, and you get the perfect square by getting these two lines down here. So that's the second of the plane shapes we're interested in. We've got a triangle and we've got a square. And these are good ways of drawing them. The other shape we're after, to look at these first three shapes and get a drink in, is the pentagon. The pentagon is an incredibly difficult shape to draw. I know of 2 or 3 different ways of doing it with compasses and a straight edge, but all of them deliver what is an approximation to a pentagon. It's close. For your eyes, it has to be really close. Honestly, if you get these things slightly wrong, they just look rubbish, you know. And this one was one of the hidden things. We know, don't we? Loads of information is kept secret from us. Well, this is one of the things that was one of the biggest secrets of antiquity. If you could turn up at certain doors and go, hey, I can draw one of these, they go, right, you're in, mate. Shut the door on you. That'd be it. You'd be on to a whole new class of learning just because you could do that. Do you see? And this was one of the things. That's how easy it is to keep things secret. This particular one, I like it especially because now we've got a 4th circle drawn here, you see. The hexagon and the square are formed in this top circle. If you want to be able to do this, and this is very nearly a perfect pentagon done by using the 4-circle technique, you put another circle on the bottom, and then this shape is kind of projected from outside itself. It's a very, very exotic shape. The same as its 3-dimensional counterpart turns out to be exotic as well. You have to do a lot more complicated drawing work to make one of those than you do to make the others. So that's how the flower of life's used to kind of to make 2D shapes, and you can see that what we've got effectively is we've got a circle with 3 circles on the left of it, or if you prefer, we've got a circle with 3 circles on the right of it, and those are enough to enable you to draw a perfect triangle, square, hexagon, and pentagon. You might have had to sweat blood to do that 200 years ago. Now you could just go home and do it. If we want to make 3-dimensional shapes and be able to draw them effectively in here, we need to have the other missing circles added. Thank you very much. So here we go. Here's the 3 circles we had before, and I've added 3 circles to that side. And now you should be able to see. Can everybody see there's a 6-petaled flower in here now? Yeah? So what we've now got is the very middle of this. Those 6 petals that you can see in the middle of there are the 6 petals in the middle of this design. Everybody happy with that? And in that central part we can introduce the first of the 3D shapes. Okay, yes, we earlier on, in order to get the vesica piscis, we imagined spirit drawing a circle around itself, stepping to the kind of the border of that circle and then drawing another circle. Now we have to imagine the spirits, if we want to get into the 3D, we have to imagine spirits a bit more sophisticated than that it's already mastered the plane thing, and that it can kind of like reach out entirely like this, and then sort of spin a quarter that way and a quarter that way, and it'll have a sphere. So in order to make the 3D, it's growing more like our cells. As we move into the 3rd dimension, we get more complicated geometric ideas. And that's very much how our cells do kind of stuff. They sort of they split up by moving to their own border and then separating. And all of these geometries effectively hold different numbers of spheres. You can actually make these geometries out of spheres as well. There's the first of the shapes that we're interested in. The tetrahedron, here it is. Just like the triangle was made by kind of leaning 3 identical lines together, the tetrahedron's effectively made by leaning 3 identical triangles together and making a 4th one on the bottom. And the thing is, no matter which way you look at this, it looks exactly the same to you. Okay? The point is that if I put a sphere around it, the points would touch the sphere but the edges wouldn't. And if I was to put a sphere in the centre of it, the sphere would kiss the centre of each of the faces, but it wouldn't touch any of the edges or the points. And that is actually the true nature of opposition. Opposition is a matter of balance. In this world, if we were to say, because we're in a polarised world, if we would say all roads lead to Rome, we'd have to say that all roads, and that's true, then all roads lead away from Rome as well, wouldn't we? You see, that's the kind of balance, and people could fight over that, and whoever it was that killed most people could say, we told you they all lead away from Rome. So, but it's also a way of dividing a sphere into 3 perfect triangles. If you were to imagine these were inflatable, these little ribs, and just to blow into it, you could imagine it being a sphere made of 4 triangles, okay? The other thing, the next most complicated shape that spirit can make out of triangles is this one, the octahedron. There it is in the middle of the flower life there. And this one, once again, if I move it around like this, same thing applies. It looks exactly the same to you because all the triangles are the same. This one's got 8 triangles in it. Once again, like all of these shapes, if we put a sphere around it, it would touch the points but not the edges. If we put a sphere in the middle of it, the sphere would kiss the centres of the faces but wouldn't touch any of the ribs or the points. This, of course, is a really rather trick shape, this one. Because it's got a sphere around it, the height here has got to be related to that. Because if I go like that, the height. Now, people tell me there's loads and loads of pyramids on planet Earth. I think there's only one, because there's only one that is like this, and that's the Great Pyramid at Giza. All the rest of them have got a much shallower angle on them. The height of the Pyramid at Giza is actually related to the size of the square base on which it sits, which means it's a geodetic model of the planet Earth. It's a geodetic model of a sphere, just like this is. Very important. Now, if you look at the other pyramids, some people try to make them this steep, but you can kind of see they start off this steep and then they go unsteep. Or they kind of start like this and they get bent. Really, nobody's made any pyramids like this apart from whoever it was did the Great Pyramid at Giza. So we've got the first of the Platonic solids is made of 4 triangles, and Plato associated it with fire. The second of them is made out of 8 triangles, and Plato associated it with air. The next one is made out of 20 triangles. This is a very exotic and beautiful shape. It's called an icosahedron, this one. Plato associated it with water. It's made up of 20 triangles. Same thing happens with the sphere wrapped around it or put in the middle of it. The curious thing about this is the water genuinely does have this kind of structure, a kind of 5-way and 3-way structure, which gives it its special characteristics, strength and fluidity under different circumstances. Now, the way I like to think it happened is I like to imagine that as spirit produced these things, it kind of came up with the octahedron and it thought, oh look, I can see a square here. I wonder what happens if I fill space with those. And so she came up with one of these. Next to the sphere, probably the thing that we're most used to seeing, a cube or a hexahedron. This is, when you get into drawing geometry, you'll find out that's why the hexagon turns up first. Because if you put the right lines on it, it's actually a cube. So there's that one, and then I like to think that as spirit made up this, she noticed the kind of 5-sided symmetry around there and thought, I wonder what happens if I fill space with 5 sides. And so she came up with this, which is a dodecahedron. This one's got 12 faces on it. Each one of them has 5 sides. Now you'll remember that the 5-sided plane was a difficult thing to draw. There's the icosahedron in the flower life. There's the cube. There's the cube actually showing itself as the hexagon. If you look, it's a 6-sided thing, but it's been made to look like a cube. Hexahedron. And here's one. Took me a while to learn how to do this. Here's your dodecahedron, associated by Plato with ether. And this time you can see what we've had to do is we've had to draw even bigger than this. If you look at this one here, we had that shape in the middle, remember, by drawing just one set of circles around a central circle. This one's had 2 more sets of circles added to it, so it's got, can you see it's got like 3 little bits at the edge here, 3 little edges of circles. Everybody see that? In order to get that dodecahedron in the middle there, I've had to go to 5. See, there's 5 circles edged here. So this is your original circle with the 1 set of circles around it, then 4 more sets of circles, and then you can draw one of these in there. And not only that, you can get the 6 to balance into the 5, which I really love. You can just, I stare at this design all the time. I've had a realisation since I did this that I felt at the time I was cheating, because you had to, in order to get this to work, you have to rub some lines out and put these extra lines in. Now I've discovered since then that if I was to make this 7 instead of 5, I can actually draw one of those in instead of faking it. And that means that just like this is the last comment on this half of the talk, just like the pentagon, the five-sided shape had to be projected slightly from outside itself, do you remember, in the four circles? In order to get a proper one of these, it has to be projected from like 4 or 5 layers outside itself, and it's the symbol of ether, which is the thing that actually underlies all of the other elements. In classical theory, all those other elements, earth, air, fire, water, are made out of ether. And the geometry of ether is just complicated enough to make us think that might be the case. So that is very well, thank you very much. Excellent, thank you for your attention. Excellent, thank you very much folks, thank you for coming back. Just before I carry on, a word from our sponsor. I have these plush DVDs that were made of the original first ever Sacred Geometry talk at the Out of the Ordinary Festival 2009, which gives you the basic rudiments of the talk, and you'll see some shapes in it that I haven't got with me tonight as well. It's also an interview at the end of it, because it's properly produced by a real filmmaker and everything. That one's a tenner. These ones are a £5 each, and if you fancy dipping into my other stuff, and it is available on YouTube as well, so you don't have to buy the DVDs, but I get expenses for doing it, and these things help keep the show on the road. This is Alchemy and the Birth of Modern Science. This is Human History, 60 million years in transition from the birth of Earth to the age of prophecy. Real cracker. And this is my first ever DVD recorded interview. I'll probably never be so honest again. So, special price, so they're a £5 each, that's a tenner, or you can have all 4 for 20 quid. Also, I have a radio show, Dr. Rock's radio show on tnsradio.com every Thursday night, 6 till 9. I have a website which does Mayan date conversions and stuff. And all of the details of that are on this piece of paper, so if you wish to keep in touch with me, you can have one of these away.
Well, you're doing it live from me.
Yes, I should be doing Dr. Rock's radio show live from here tomorrow evening, hopefully. Always good for a laugh. Right, well, there's lots of odd stuff in the second half of this show. There is. So I might as well crack on, I think. The see which one we're going to... Okay, right, yes, here's something that I should have probably put on. Oh, there we go, yeah. Unfortunately, a lot of them are missing. Oh, there we go. Oh, yeah, it went one further. This is what happens. I put this one up again, some of it's missing. That is what happens when you connect all of the centres of that design over there. And it's a thing called Metatron's cube. It's actually the subject of a talk all on its own. It's a bit of a shame that a lot of it's missing. But every single shape there is in there. And that's why this is such, that's why that flower life, that circles on circles is such a potent design. If you go to somewhere like the Alhambra in Moorish Spain and you look at all the astonishing geometry on the buildings there, you see some really quite Art Deco stuff. You know, some of it looks really 1920s, 1930s. And underneath all of it is that key. This flower life, this circle on a circle is what's underneath all of it. You can even get the knotwork. If you'd looked at it earlier, you'd have seen that there's some of the Celtic knotwork is expressed in this, which is interesting because our ancestors used square grids. They used interfitting square grids to come up with these designs. But this is the Arab way of doing it. And basically, underneath nearly all of those designs is this circular thing. Now, it looks like an easy thing to do, perhaps, to come up with just circles on circles. Just remind you what it looks like. But to make something that balanced really takes a bit of doing. You have to work several techniques because it all goes wobbly and stuff. But I thoroughly recommend, if you don't try anything else, try that. Because really wake up your inner geometrist, or geomatrix if you're a lady. Can I have the next picture? Yes. Now, although we were calling them Neolithic pictures, unfortunately, 2 of these are missing. We've really got to get to be able to wrestle these Macs to the ground and teach them how to show a JPEG. I normally use Linux open source software. These are Neolithic. These came from Skara Brae, which is like a... Has anybody heard of Skara Brae?
I've seen those.
Have you? Where were they?
Orkney Museum.
Right, yeah, exactly. Brilliant. I've got a really fantastic little book about Orkney. It is full of really interesting places. And one of them included what looks to be a kind of underground, like retreat house or collection of houses. Several of the rooms are related. There's like a sort of separate room, which is where we don't know what went on there. There's evidence of bead making, blade crafting, and it looks like the place was left in a real hurry. There's like kind of broken bracelets just trailing out the door. And the furnishings for these places are all made out of stone. Stone tables, stone seats, stone baths, all kind of like they're expecting it to be swept away at any minute. And they did these. They did these Neolithic platonic solids. And all of them are there. This one you can see it's a dodecahedron. This one, you can see it's that one. You can see that this one is the icosahedron, which is that one. So although we call them platonic forms, and Plato was about 600 BC, I think, these are probably a lot older. In the Ashmolean Museum in Oxford, there's actually a crystal set. Really nice. I don't think they display them anymore, but I think that if you really ask nicely, they might show them to you. So that's just to show that although we call them platonics, they obviously were a lot older than that. These have been part of our knowledge base for a long, long time. Now, these pieces that we met at the beginning, they look like they're kind of completely independent pieces, but in fact, if I ask you to do a little bit of mental work on this one's got 6 square faces on it, and if you imagine that each one of them has got a spot in the middle of it, like a 1 on a dice, so there's a dot on the centre of each of the faces. And if we imagine then that this dot on the top is connected by beams of light to the dots on these 4 faces, and we imagine that this dot here is also connected by beams of light to these 4 faces, then what you should be imagining is one of these. So the points of this point exactly into the centres of the face of this, which means that in a way this is a kind of etheric counterpart for the cube. The cube and the octahedron are related to each other. Obviously the same thing applies to this. If you look at this as I point it at you, you can see that there's 4 triangles there. So if I was to put a dot in the centre of each of those 4 faces and join them together, you'd have a square, wouldn't you? And because this thing's got 8 triangles in it, you'd end up with one of these. Next picture, please. Very good. So now the corners of this one point into the centres of the faces of this. Now, in this particular example, let's call the octahedron, which you can't see fully, the container, because it's got the cube in it, and we'll call the cube the content. If the content grows so that its edges are as long as the edges of the container, then you get a wholly new piece. You get the marriage of earth and air, earth and air. And I've got the model for that one here. I have. There it is. Yes. The model for earth and air, you can see that this one here is like that. You can see that there's a cube here and there's an octahedron. Everybody see that? You can come and have a play with them afterwards. I'm going to give it a quick spin as well, because what this should be imagined is as like a frozen waveform. It's actually more like an oscillating thing. I think they're much better if they're imagined like that. Now, the thing about this is that it has in the middle of it one of the shapes that we're going to be interested in next. Because whilst all of the shapes we looked at in the first half divide spheres into identical portions, so 3 of them divided them into triangles, 1 of them into squares, 1 of them into pentagons, what we're going to see this time is that these shapes divide spheres into 2 or more different shapes. Now, this one is our marriage between earth and air, the octahedron and the cube. And one of the things I'd like you to notice about it is if I hold it like that, you can see that what you've got is a big triangle pointing upwards with a little triangle upside down in the middle of it. And that one of the first things we looked at, the big pink triangle with the orange triangle in the middle of it, that just comes up again and again. A triangle with an upside down triangle. That's one of the things about this shape. The other thing about it is that if you remove all of the points, imagine all the points are missing. If I point it at you, you can see there's a square in it there. Can everybody see at the base of this point is a square? It's got 4 ribs, so that must be the case. Okay, and if we then look at underneath these points, this point here is surrounded by 4 other points, and underneath them is a triangle. Okay, so we have a shape in the heart of this beast which is very much like that. And this is coloured in green and yellow to show you that it grew from earth and air. It sits at the heart of earth and air. And these are called feminine forms because they actually involve 2 different shapes in making up a form, which means they've got to cooperate and get on with each other. 2 different things have to cooperate to make the one new thing. The other thing is that the feminine force is a binding force. So when you look at crystals, we are actually going to see a little bit later on that crystals form shapes like the platonic solids. But when you look at their bonding forms and their atomic structures, they quite often show you shapes like this. So once again, the geometry is actually related to the physics of the real world. And we can now see that the cube and the octahedron are reflections of each other. And at the points where the cube and the octahedron meet, where the 2 masculine forms meet, we get a new feminine form. The first of 13 feminine forms that we're going to get to look at. Now, that pattern is actually repeated. We're not going to go into it in too much detail. You can look on the internet because sometimes I do go through these bits of it a bit more slowly, but I'm not going to tonight. If I put a dot in the centre of each of the faces of this, then what I'd get in the middle is one of these, an octahedron. So the same thing as the cube and the octahedron, the icosahedron and the dodecahedron. If you don't believe me, here's what I shall hand round. This one has got one of these on the outside, a purple one on the outside, and on the inside it's got one of the blue ones. So it's just to show that what I'm saying is true. There it is. You can see that the points of the icosahedron, the sign for water, are right in the centre of the faces of the sign for ether. So the 2 universal growth media are also reflections of each other. The same thing applies to this. If you look at it, it's got 5 triangles meeting there, so if you put a dot in the centre of each of those triangles and join them together, you'll have a 5-sided shape, just like one of these, which looks like that. So that way, the points of this are in the centres of the faces of that, which is, I think, a really nice kind of interchange. You can imagine one forming inside the other forever and ever. Actually, all of these shapes do nest inside each other in really sexy ways. It's just that this is a particularly important theme to follow. Now, the same thing applies if we call the dodecahedron, which is this one, the content, and we call this one the container, and we imagine that this one grows until its edges are the same length as the edges of the container, then we get a wholly new shape. Once again, the marriage of earth and ether. I don't know what, of air and ether. It's the marriage of water and ether. Do shout out when I'm screwing up, folks, I'm just testing. I have got a model of this one at home which looks very much like that. And the same thing basically applies. Although I haven't got it with me, when you look at it, if you hold it up and look at it this way, you can see that it's made up of a big triangle with a little upside down triangle inside it. So we've got another shape. It's made up of the same kind of planes all lent against each other, but to make a different form. The other thing that also applies to that one is that if you imagine the points being removed, like we did with that, you end up with a new shape, this one. So sitting at the point at which the dodecahedron and the icosahedron meet is this, which is an icosydodecahedron.
Say that again.
Icosydodecahedron.
3 times fast.
And it's made up, that one was made up of triangles and squares as a way of dividing up a sphere. This one's made up of triangles and pentagons. So you can see what's going to happen is all the different combinations that we had the first time round are going to turn up now, but kind of like mixed and shuffled. The important thing to bear in mind about these, and you will see this in a photo a little bit later, is that these things are growing in size as well. If you look at the size of the ribs on that, the length of the sides, they're quite long. I obviously had to fit all of these onto A4 sheets of paper, so the edges on this are quite short. All the edges are the same length, but they're short. So if I made this out of something this size, this would be a lot bigger. So as we work through these progressions, as well as getting more complex, they're getting bigger. But they're still only using triangles and pentagons. And of course your pedant could point out that you could turn the pentagon into triangles as well. And when you look at modern engineering software, stress analysis software, what it does is it takes a model of, say, a bicycle, or I don't know, the hinge on a ferry door, shall we say, and it breaks it down into little triangular elements and then subjects them to force to see how quickly it's going to break. So we've come across two of the shapes that I'm interested in the second part of the show. One of them is made of triangles and squares and is the marriage of earth and air. Adam's earth it's sometimes called. The other is the marriage of water and ether and is made up of pentagons and triangles. Now, I'm not quite sure what happens next, but we'll just have a quick look and see. Okay, yeah, that makes sense. Yeah, thank you very much. That's good, obviously. That's why you do it in advance. Right, missing off over there is one of these. We've returned to this. We've looked at these two sets of reflections, and that leaves us with the symbol for fire. And if you put a dot in the centre of each of those faces and join it to those, what you get is a little upside down tetrahedron. So fire is a reflection of itself, which I really like. Also, if you imagine that content grows until its edges are as long as the edges of the container, you end up with the shape that actually turned me on to sacred geometry in the first place, the star tetrahedron. A genuinely, absolutely astonishing piece of tackle, that one. Really. I haven't got the wire one with me, unfortunately, but this one will do. I did try to make this so that it's got a blue pointing upwards and a red pointing downwards, but so far it hasn't worked. So I've just stuck shiny little reflective critters on the upward pointing one and not on the downward pointing one. So hopefully you should all be able to see that. What we've got is one tetrahedron pointing upwards and one tetrahedron pointing downwards. We imagine that one growing, but you can imagine them just interpenetrating each other. The thing is, this is kind of like your first piece of hypergeometry. Hyper means like above, the level above. So a cube is a hypersquare, if you like. That's kind of simple explanation. The thing is that as that tetrahedron grows inside its container, from the moment its little baby tips come out of the centre of the triangular faces, they're going to be tetrahedral. It always is an echo of itself. And this proved to be quite a frustrating shape for me when I was... Because once I'd made one of these, I thought, what I'll do is I'll make a great big tetrahedron and then I'll make 4 small tetrahedron. All this takes a fair bit of time. If you're actually going to make them on the computer and colour them in and print them out, cut them out and all of that, it takes bloody ages. So what I actually got was one of these, of course, because these things are half the size of the big thing. Just like that triangle that we looked at the beginning with the half-size triangles. Basically, the little tets that you can see sticking out are half the size of the big tets on. So when I did that experiment, I ended up with one of these, which cheesed me off a bit. If you look at the wire version of one of these, you can also see that in the middle of it, because there's a point here and here and here, and what you've got in the heart of this is one of these. And I discovered that because what I did was I thought, I wonder what happens if I make some tetrahedrons that are the same size as these triangles here. So I made one of these and I made eight tetrahedrons and stuck them on, which took another good day's work. I've got another one of these. That's why the star tetrahedron is such a key, it really is a central piece of tackle. Turns out to be central for other reasons and a little bit as well. It's also important in terms of ideas because we imagine that the upward pointing tet is the mother of form reaching up to the father of consciousness that's reaching down. So you've got the two tetrahedra mixing together, the mother of consciousness, mother of form reaching as the father of consciousness reaches down. And that's what the earth does in the morning as the sun rises. That's consciousness, data, information, energy, light coming down. And earth, matter, mater, the Latin for mother, is where matter comes from, reaching up. You can see it. Hear the birds singing, see the plants reaching up, see the steam rising in the morning. This is a symbol of all of that. The perfect balance of the masculine and feminine. The total proper balance in symmetry of opposition, of polarity. It's where we're supposed to be. It is the symmetry that we're all reaching for, and probably the symmetry of consciousness that we're about to achieve. What we're experiencing at the moment is polarity that's kind of like working more like a fractal. It's asymmetric. It's what happens when the things don't quite fit together. But that's part of the experiment. It's just, this is oneness as oneness. This is oneness as many things. And this is where we're going. Very, very beautiful shape. Fire reflected on fire, and if it's got one of these in the middle of it is air. Which is, again, really great. because of course fire really needs the air to burn. We're going to really rush through these other 13 shapes because it's not particularly important, but what is amazing is that they all grow from the basic principles that we've already seen. We've seen 2 of the 13 so far, the 2 that are born at the marriage of the cube and the octahedron. That's the cube octahedron, and the icosahedron. There's 5 shapes that are sort of shuffled in amongst them, and I'm going to deal just with this one because this is really easy and it is a general principle. You can see that there's similarities between this, the masculine shape, and this, the feminine shape. It looks like somebody's chopped the corners off one of these to make one of these, which is why the physicists call this a truncated tetrahedron. Tetrahedron with the bits cut off. And of course that's something we see in the Bible, don't we? We see that you make a woman by pulling a bit out of the globe. It's the same thing. It turns up in all the other books as well, and it's even there in the way they name the geometry. But one of the things that I've had physics people and mathematicians and geometrists even to this talk, and none of them have given me any trouble, and the one thing that really surprises them is the thing I'm about to tell you now, because they always assume that this is a diminution of that. That doesn't make any sense, does it, considering we're looking at growth. That's what we're looking at here. And in fact, here's one of them. This has got both forms in it. Look, you can see it's got the tetrahedron, and then it's got the truncated tetrahedron in the middle of it. Now, if I point this at you, there's 2 sorts of growth involved in getting these shapes, and the first type of growth is when the ribs just move apart from each other until they're as far apart as they are long, and then they join up the resulting points. Now, there's 3 ribs pointing at you when I point that at you. So if those 3 ribs move apart until they're as far apart as they are long, they're going to have a triangle in them, aren't they? Yes, they are. Very good. And if I turn the other end of it around, because it's all identical, the same thing would apply to the other bits of it. So you can actually grow one of these from one of these. And that comes as a real surprise. That's enough to send your geometers rushing for their books to dust them off again. But they won't find that written down because for some reason the story's been told the other way. Just like the story of Adam's rib. Very odd. But of course, originally, the Genesis story didn't do the Adam's rib thing. The original Genesis story had Adam and Eve being created at the same time. Which is what the true geometry probably reflects when we look at the story. Anyway, however it falls out, this is not a truncated tetrahedron, it's a grown tetrahedron. And it's made up of hexagons and triangles. And the same thing absolutely applies to these as well. Basically, in order to get a truncated octahedron, they've chopped the corners off. But the same thing applies. If I point 4 things at you and they grow apart till they're as far apart as they are long, and you join them together, you're going to get a square, which is what's on this. This one is a marriage of squares and hexagons, and is the feminine form of ether. Same thing applies to the cube. Here's a truncated cube, as it's called, and or truncated hexahedron. And this one's made of octahedrons and triangles, so it's actually gone one step further. Do I get that now? I don't. Oh, I see. Okay, I'll do that in a bit then. Same thing applies to this. This is a truncated dodecahedron, and it's made up of octahedron and triangles. And here's one. This is the one, the icosahedron. This is hexagons and pentagons. So what's going on here is that these shapes are basically still using the same shapes they used before, triangles, squares and pentagons, or as it turns out, as they get more complicated, they also use 6-sided shapes, which is twice 3, 8-sided shapes, which is twice 4, and 10-sided shapes, which is twice 5. So once again, they've just kind of doubled up, twisted round a little bit. There is nothing very complicated going on here, and yet all of these shapes are being generated simply by self-reflection. And effectively what's going on, if you imagine the sizes of the ribs not changing, all we're talking about is the repetition again and again in different forms of that original line. Do you know? That original extension into space, the original establishment of polarity, all of that. All of these are stacks of single lines in really intelligent ways, really interesting ways. Now, the next way they grow, and I don't really want to spend too much time on it, what happens next? The other way you can grow is instead of growing the ribs apart and joining them together, you can imagine that the faces of a shape grow apart instead. So we might imagine that the squares on this move apart from the triangles and the other squares move apart from the triangles. And you can then join the varying shapes in between. And when you do, you get one of these. So this one again is coloured out yellow and green to show that it grew out of earth and air. And what this one does in its next stage of growth, and we are going to see other versions of this, which is why I'm hurrying, is that it goes back to its original form of growth. And this one, once again, the ribs move apart until they're as far apart as they are long. And when you join them together, you get this one, which is one of the first shapes that makes the sphere into 3 different shapes, this one. It's now got to the point where it's using 6, 4 and 8-sided shapes. But it's all grown from that original cube and the octahedron, from those original shapes. And these, of course, will be getting quite big, as we'll see. The same thing actually applies to these ones. This one here. The pentagons and the triangles slowly but surely warp outwards, move outwards until they form this really nice shape. And see how much like a sphere it's getting, this one? This one's made up of squares, triangles and pentagons. So it's made up of the original shapes we were looking at. And you've got lots of faces on that. I can't remember how many there are. And that is that's a rhombiicosydodecahedron, that is.
Did you say so?
Yeah. Prove me wrong. And then this one, right? This one then does the same thing as that last one. We then goes into the original form of growth again, and it moves its ribs apart until they're as far apart as they are long. And when it joins them, it comes up with this one. And this is a great rhombiicosydodecahedron. And this one's made up of octagons, hexagons, and squares. So we see these in a minute all together so that you can see how they are variously related. In the process of all of that, there are only 2 of these. There's only 2 more of those shapes to look at. And one of them is coloured the shape of the colour of ether, and one of them's coloured the colour of earth. And that's because these are the only 2 single elements that kind of grow beyond the second level, if you like. And they do it the same way. Their faces move apart until they are as far apart as their edges are long, and then they're joined together. And the results are the same in both. One of them ends up with squares, the shape of the original cube, totally surrounded by triangles, and this one ends up with the original dodecahedron, again, totally surrounded by triangles. So once again, it's like another kind of uniform solution that it's come up with. But these ones are really interesting. They look just like the rest, but if I hold them up, you can sort of see that the squares are not all aligned in the same way with each other. They're actually easier to see on the wire ones. But the squares are slightly skewed, you see. They're not quite square, and you can't make them all square, and that's because these 2 shapes here, which are the expansion of earth and ether, have got left and right-handed forms. So although they are symmetrically dividing a sphere into pentagons and triangles and squares and triangles, you can actually have 2 different forms of these. You can have a left-handed one and a right-handed one. So there you've got asymmetry built into the symmetry, which I really like. And as a result, they look quite different from the others when we spin them. So that's how the shapes grow, and we'll go back to them when we've dealt with this bit here. This is a picture of a fern growing, and it's going to introduce us to the only bit of arithmetic we have to do, because it's demonstrating a little progression called the Fibonacci sequence of numbers. And the way they work is the first 2 Fibonacci numbers are 1 and 1. We'll see a picture of it in a minute. And when you add 1 and 1 together, you get the next Fibonacci number, which is 2. And when you add 1 and 2 together, you get the next one, which is 3. You add 2 and 3 for the next one, which is 5, 3 and 5, 8, 8 and 5, 13, 13 and 8, 21. It just goes on like that. And that is the number that you're going to see everywhere in nature. And this is how it looks. If you look at this here, this curl is actually going to turn out to be exactly a Fibonacci curl. And when you look here, you can see that the little leaves are also going to unfurl in exactly the same way. They're going to have exactly the same Fibonacci curl to them. And as it happens, the fern is a completely fractal device, because these little unfurling things here are going to be really tiny models of the giant unfurling thing that is the whole leaf. When you look at ferns, that is one of the things that defines them. Can we have the next picture, please? And here's a picture of how it works. There's your picture of your fern, and here's a thing I have constructed using the Fibonacci principles. Once again, we're losing a little bit of it. But what we've got here, right in the middle here, is a little square which measures 1 by 1. And that's where, and then you draw a little arc in that square, just from one corner to the next. And then if you take 1 plus 1, it gives you 2. And the next rectangle is 2 times 1. 2 times 1 is 2 plus 1 is 3, so the next one's 3 times 2, next one's 5 times 3, next one's 8 times 5, next one's 13 times 8, next one's 21 times 13. And each time you draw in this curve. And this turns out to be almost a subject all on its own, the Fibonacci sequence, which is why I didn't really put it into the original talk. I thought, rather than only skimp over it, I'd not put it in at all, but I think that was an incorrect decision. The actual number down the explanation of it on the bottom actually tells you that it's the perfect way of cutting a line in two. Basically, it's a way of finding a point on the line such that the long bit of the line is 1.618 of the short line, and the short line is 0.618, and it works all the way down. Like, this is 1.618 of that, this is 1.618 of that, this is 1.618 of that, this is 1.618 of that. And it works for my body, it works for where leaves are on plants, it works for the shape of frogs, it works for the shape of fish, even a river. You know how rivers meander? Its length as a meander will be 1.618 of its straight length. It is absolutely everywhere, this particular set of numbers. And the thing is that 1.618 is what you get if you divide 8 into 13. But it's actually one of those magic numbers like pi that just goes on and on forever. And the bigger the numbers you get, the bigger the Fibonacci numbers you use, so 8 and 13 will yield a number nearer the perfect value. It's a fantastic way nature's found of filling space. It is. Here's another way of things growing. This introduces the Lumino brothers, the artists previously known as the Grey Twins. They're in there just to show you how big these things are, because this is a game that we found which is absolutely fantastic. This is Geomag, accept no other. If you go for it, it's an expensive hobby. You see really jealous making things on the internet. I think we've got rooms full of it, but I haven't. And this is one way things can grow. This is one way things can grow. They can just grow like an onion by kind of basing themselves round the thing in the middle. This is how big your original tetrahedron is, which can be imagined as a kind of original cell. It's got one length of stick in the side there, then 2, then 3, then 4, then 5. And it fairly quickly gets itself some sort of profile by doing that. We have the next one of those. Here's another way of doing it. This again is going to prove to be rather frustrating, I can see. We have here one of the original little tets with one of the Lumino brothers sitting next to it. And what this is it's 4 tets, like that. You put 3 next to each other and then you put 1 on top. So this takes quite a lot more poles than that does. And what that one over there is 4 of these. Stick 3 of them together, put 1 in the middle. And what you're getting is a bigger and bigger upside down hole, the shape of one that is in the middle. We have the next picture? I don't know how much
So
it
what did
was.
you call this?
This one is called a Sierpinski sponge.
You are.
Yeah. What do you call the sort of bits you stick together?
Geomag.
Geomag.
Geomag. Geomag. Yeah, it's magnetic sticks and balls. But they are strong enough. You can make a star tetrahedron. You can make one of these. You can put a magnet on a metal mantelpiece. And you can actually hang one of these off it and spin 2 balls to ball. So you've got more or less a frictionless bearing. And when you do that, if you put other shapes hanging along the same piece of metal, they will get interfered with by it. It's an unbelievably great game. But there's one called magnetics, which isn't strong enough to make magnetic forms. If you make anything bigger than the platonic shapes, they just fall apart. Here's your next one. This one's made up of 4 of the big ones that we had. So Well, look what you're getting here now. You've got a space in here that is actually 4 bars big. And I saw, so I ran out of bits then, because you need 4 to make the first one, or whatever it is. If you need 4 to make the first one, you need 16 and a bit, 16. It just goes up really quickly. But I saw one where he'd gone 2 layers more than this, so he'd got a Sierpinski sponge made out of geomag that was having, and the next one of these would be 8 across. And you literally pick it up and just sit it on top of the others. It's ever so pleasing it is. So, and that's the tetrahedron. Remember how we kind of raved about it in this form? About how kind of no matter how you look at it, there's always a tetrahedron, and you can stick them onto an octahedron, and you can stick small ones onto a tet. Well, this is the same facility, if you like, for the tetrahedron to grow as a kind of as a hyper thing, because everything is based on triangles, really. What's he going to show us next then? Okay, there's a cunning drawing. That's the picture of how. You remember how I said it was using as well as using 3, 4, and 5-sided forms to make these more complicated shapes. It also uses 6, 8, and 10-sided. Well, I found out how to get the 8-sided one. This is all done out of the 4 circles. You can get all of these 2-dimensional shapes out of the original 4 circles as described. But I haven't worked out yet how to make, I bet you can, but I still can't work out how to make the 10-sided one out of this. So anybody knows, come and see me afterwards. Yeah, here we go. Here we see the way some of these things are related and how they grow in terms of the height of the Lumino brothers. Here's an octahedron and a cube, which we all remembered were kind of married to make that rather spectacular thing. In the heart of them was the cube octahedron, which is that one there. And then we remember that the cube octahedron grew into one of these, which is that one. You can tell it is because it's got squares all the way around its vertical meridian and around its horizontal, just like this one. The only time you'll have seen these, the Moroccans make lots of candle holders in these shapes. You won't generally see these feminine shapes around the place otherwise. And the next picture is going to be excellent. Yes, look, it's one of these sitting inside one of these that's forming. So what we've got is in there you've got the squares around the middle and around the middle and the triangles in between the squares, just like that one. And then forming on the outside here, projected straight out from this shape, you've got a 6-sided shape there, which is what's in here. And so this green shape that you see forming here is going to end up being made of hexagons and squares, and octagons. There might even be one if we're lucky. I'm not sure it happens now though. Oh, it does. Great. Well, somebody, obviously the pictures have been in working at my slideshow. So you can now see in the middle of that, in the middle of this shape here, which is one of these, is one of these. You can see them nestling inside there, just like that. They're ever so pleasing to build. Once again, I've built them and taken them apart, and it's still sometimes really frustrating because you have to point all the magnetism in the right direction. Otherwise, on these big shapes, you kind of get towards the end and it goes snick. And then you've just got to take it all apart, and then it's a pain in the arse. Then you can be really glad that you don't have a room full of geomag, because when 20,000 bits of it collapses, I bet it takes a family ages to put it all back in its box. Next picture. There we go. Yeah, look, that's the biggest one. There's the Lumino brothers expressing themselves fully in front of one of these. Okay, really fantastic shape. It took me ages to work out how to do this one. And no matter how much geomag you bring home, you kind of build the next shape and you go, I've bloody run out. So, and this one again does both jobs. The yellow shape in this one is made up of octagons, hexagons, and squares, which is not that one. I must be wrong. There must be decagons, octagons, hexagons. Yeah, hexagons. There it is. Hexagons, octagons, and squares. I'm getting thirsty or in need of chips or something. I didn't even believe my own models there for a minute. And that's the trouble with this. It doesn't matter how often you do it. It's really difficult to get it so that it never really comes easily. Well, it doesn't to me anyway. And in the heart of this, The green ones here are actually being used merely to separate this shape, which is made of triangles, squares and pentagons, from this shape. So the red one here, that pentagon you can see there is basically one of these, and this is the square. This is one of the squares, that's right. It's oh no, that's right. If you could see into the shape, you'd see the whole thing inside there is one of these, and it's projecting one of these outside itself. What's the next picture then, Svenja? This is showing the build-up towards that last shape, so they're not quite in the right order yet. This one should have been before the last one, because that's the shape that's sitting in the middle. It is. There you go. And again, you can see that last one was pretty big. You're actually big enough to put your head inside that last one, or my head. Next. There you go. See, you can't see all of them. It's a bit of a shame. It's been mapped. But you can see the cube over there is a small one, and the octahedron, the cube and the icosahedron, then the cube octahedron, truncated tetrahedron. So they're quite mixed, but there's the big one. The big one you can see, it's a really big thing like that. And these obviously are mine. I haven't got enough to do that, but somebody on the internet has. This is how nature actually uses some of these shapes. Up there is a piece of rough garnet, which is exactly in the shape of an octahedron. Exactly in the shape of one of these. That's a piece of magnetite, which is all broken, but it obviously was once an octahedron. This is a piece of iron pyrites, or fool's gold, in the form of a cube. It's not actually quite in the form of a cube. I cheated with the photograph. It's actually slightly longer on one side than it is on the other. But I did see it come out of a big lump of iron pyrites that was the same proportion as it was. So there it was, making itself into a kind of cubic thing, and just splitting off this little bit of a cube, just specially for me, which I thought was really great. But the iron pyrites doesn't only do that. The iron pyrites also does. Let's have the. You can see that nestling in there is one of these. Can you see in there? If you do the next one, I think the next one might show it a bit better. It might not, because it might be missing. It is missing, so you can put it haunted up here. Actually, it's got two of these kind of just sitting like there's that much of them sticking out the top of the iron pyrites. So the iron pyrites does the square, and it does this as well. And it also, when you can see it properly, it brings us to an interesting point that you don't very often get these pentagons perfect in nature. They're nearly always slightly off. And that's one of the things about all of these shapes, is that they're templates. Nature actually makes itself by being slightly different from it. Not too different, but slightly different from the templates I've seen. One or two other interesting things that we can see about these is that if we have a look at this one, looks like something that we haven't seen before tonight. And if I hold it on its side, hopefully you can see that it is actually two of these stuck together. You can see that there's a star tetrahedron here, and there's another one here, and they've been wedged together. I've normally got to wire one of these with me, but if I put that on there, you can see that more or less the same thing is happening. Now, the crucial thing about this is that where these two things meet, in the middle, if you look, you can see there's a square pointing towards you, okay? And if you look around the edges of the square, you'll see that there's a triangle on each face, and that there'll be another square in the middle of the triangles. So it should bring to mind this shape, the cube octahedron. So sitting at the heart of two tetrahedra is the cube octahedron, which turns out to be a pretty important shape, because there's two ways of looking at it. We can imagine we've got a whole set of these at home. We've got a set of stars that are made out. We've got one for every single one of these shapes. Okay? So the star that makes this up is just a really astonishing piece of kit. But this star here, which is the only one we've got with us, is based around one of these. So imagine one of these with rays going outwards. Here is a cube octahedron. It's got the squares and the triangles around it. But this one's got all of the rays pointing inwards. Okay? Now this is when you're starting to actually look at the shape of the sub-ether itself. This is what sits at the heart of two star tetrahedrons, which, if you remember, is this magical piece here. So when you stick two of these together, you get one of these in the middle. This one is imagined to have its rays pointing inwards. The reason for that is that when we stick two lots of this one is effectively 6 of those. It's 6 of these stuck together in a cunning fashion. So right in the middle of this shape, if this shape is one of these. Okay? But this we're starting to get.
Oh, pretty.
Yeah. These, when they're lit, we sometimes have them lit with spotlights at 4 corners, and then they throw shadows inside themselves. So you can start seeing how we might get a matrix out of these basic shapes. All we're talking about here is 2 shapes: the star tetrahedron and the cube octahedron with its stellations, if you like, going inwards. And what we end up with, or we start ending up with, is one of these. Now, pretty soon I shall be able to get back the next one of these, which I dropped. It's a great shame, because the next one of these actually covers it in a skin. It adds more triangles to it. And what we end up with, in fact, is a giant star tetrahedron with a giant cube octahedron wrapped round it. So it's one of these, and it's nestled into one of these. And building all the way to the centre is a whole stack of those, which are effectively expressions of the star tetrahedron itself. So unfortunately you can't see that intermediary step, which is basically a giant cube. If I hold it one way, it looks like a big star tetrahedron with lots of fantastic stuff going in, and if you turn it on its side, it just looks like a cube. So it's like a holographic representation of this. This is the little thing that sits at the core of the whole job. And we luckily do still have the next bit, which shows just how it all relates together. This bit we really don't carry about very often. Okay. Pretty. My precious.
Wow.
Now you won't see very many of them. But there's several things about it that are really quite important. The first thing is that, as I hold it up to you, you can see that there's a square there, can't you? And that there's triangles all the way around it. Yes? So essentially, it's once again, it's one of these. It's a cube octahedron. More importantly, it's this one specifically. Actually, at the heart of this is a little stained glass one of these. When you look at it, you'll see that right in the middle there's a little cube, and you can see there's stained glass just round each one of these bits. So it's related to the cube octahedron, but of course, most amazingly, it's actually made up of 6 of these, all lent together in a pretty ingenious fashion. So it very neatly ties together almost all of the principles that we've been looking at from the beginning. And really it is just tied into those early geometries. So I'm gonna see if that'll hang off there. No, I'm not.
It's only one way.
Because I've got 1 or 2 things I want to show you just before we finish. There's a few trick things to. But that's a pretty amazing tale. I think we were really surprised because it took years. It took us a total of 7 or 8 years to go from discovering that the geometry had anything to do with us to actually getting to these pieces, of geometry. And it was a real voyage of discovery as these things kept coming over from Bali. Just more and more beautiful things. No, it's not going to do that, unfortunately. Never mind. There you go. I'll give you another spin of it now before it goes back in its box. Here we go. It's got everything in it. It's Metatron's cube in 3D.
Yeah.
That's what it is. It's that Metatron's cube in 3D. Everything is in there. And before they made this one, they actually made a cubic one, which is really brilliant. It was like a kind of noughts and crosses thing, but in 3D. And what they've done was made it out of silver, and around each silver bar they just put the edges of the circles, and then they put little bits of glass in there. And the way it worked was really clever. You had to look at it, you had to hold it up like a cube and look at it through the corners, look corner to corner, and when you did that it made a sphere in your head. It just made a sphere, made one of them in fact. So hypergeometry, there's all those different shapes all nestling together, you see. There's all those different shapes in there, but ultimately it's all down to the cube octahedron and the star tet. So what there is a whole load of really, really complicated things in there, all leaning together in a pretty intricate form. But the actual basis of the whole thing is still only a single line, repeated again and again and again, and lent up against itself in a rather special way. And that's the essence of hypergeometry. You always lose something when you're bringing it through, apart from the star tet. I've only got one really to demonstrate here, because I forgot to bring the tesseract with me. But this is a good way of demonstrating hypergeometry, because it's a dodecahedron, and in it it's got 5-pointed stars put into the centres of the faces. And it was made because somebody asked us why it was that we were saying that the cube was associated with Earth, when John Dee, who was Queen Elizabeth's sort of astrologer and necromancer and what have you, said that it was the dodecahedron. So somebody had the bright idea of making one of these. And it's really great, because if you put your index fingers on either end of one of the bars of one of the stars, and put your thumb at either end of one of the others, what you get is a square. Okay, so there's a square between my index fingers and thumbs. If I then put my ring finger underneath my index finger, I can define another square. And with my little fingers on the other side, I can make another one. So what I've now got is a cube held within the dodecahedron. And you can then move your fingers round and demonstrate to yourself that there's actually 5 cubes hidden in here. And we actually spent quite a long time trying to get needle and thread through so that we could actually just put one face of each of the cubes in. But it turned out to be too much trouble, so we have to do it. So that's a little bit. Well, you normally got a tesseract as well, which is like 8 cubes all squashed together, and you lose the form of them. But well, I'm not going to do that now. What I'm going to do is move on to a little bit of. What can I do with those? Where are my Mubus strips? Can I put them around the back?
But now 5 minutes and we've got a bit of Q&A.
Yeah, brilliant. Oh, there they are. Look, yeah. No, we're just about done. I'm now going to, having done a bit of hypergeometry, we're now going to look at what happens even with flat geometry. Where are those scissors that that nice gentleman lent me, aren't they? There they are. Because this, for example, was one of Vicky's TruthJuice posters until I cut it into strips and then sort of sellotaped it together. This one's just a normal hoop that I've put together, and when I cut round it, it's going to do pretty much the obvious thing, which is to just fall in two, which is exactly what we'd expected to do. Really weird stuff starts happening, however, when you start putting half a twist in the thing. This is called a Mubus strip, and what it does is it turns a flat thing. It's just a plane before I did this to it, technically. But now I can run my finger round and round the white side of it, like this, round and round the white side. It's still on the white side there. And then eventually it comes onto the coloured side. And if I continue to run it along the coloured side, it eventually comes back to the white side again. So this flat thing has become distinctly weird just by having like half a turn put into it. And if we now take the scissors and cut it in half, what do we suppose is going to happen? You've got to remember there's twists in things like galaxies and ribbons of stars, and there's loads of twists in us. Loads of twists. There we go. What it does this time is instead of falling in two, it actually makes an infinity sign. That's bigger than it was. Now, what I used to say was that if I had an infinitely sharp pair of scissors, I could actually go on cutting this forever and ever and get a bigger and bigger thing. Which, because you can, until one lady came up at the end of the show and she picked up the scissors and she picked up one of the Amoeba strips and did what I'm doing now. We did hear a story about a young lad that bet all of his mates in a schoolyard 50p that he could cut his way into a postcard in such a way that he could just step through it. And obviously the idea was to go and see all of the kids and get 50p off each of them and then prove that he could do it. And I thought this was the technique he used. In fact, Rhian has shown how you can cut a postcard so that you can step through it. She did do it. This wasn't the technique he was using, and we're just going to find out why that's the case. It's because when we get to the end, what happens this time is it falls into two. It falls into two infinity strips. Okay, so it doesn't behave the same way twice, that particular one. You can have a lot of fun by cutting the next bit up as well, but that's not quite all. That's the penultimate stunt, but this is the ultimate stunt. And this one is slightly different in that it's the same thing, it's got half a twist in it, but this time I'm going to start cutting it on your left, my right, and I'm going to stick with it, try and stick with the left and right. I did used to think I was a good Blue Peter kid, but they said that if I was, I'd have had one that I prepared earlier, which is a fair point. So what's happened now is I've got round to my original cut, which is here, which was on my right and your left, and now I'm still on my right and your left, even though I've not come across that. So if I carry on going round and round, I have to move them out of there and complete the cut. And remember, this is just a piece of flat paper that's been kind of like turned over, just half turned over. Imagine what it's like on kind of cosmic level, because this sort of stuff happens out there as well. Where are you? You're that. This time what I've got is a little loop and a big loop. So by cutting it halfway across, you get rather a strange effect as well. And then what happens is if you cut that one in two and this one in two, they do different things. I think this one gets twice as long as itself and this one becomes two or something. But there's actually a lot more things you can do with the Amoeba strip as well. But that shows you that even when you go back down to just like a flat thing and start seriously looking at it, there's something slightly fishy about the whole deal. That's what I reckon anyway. Thank you very much for paying so much attention.
I don't know about you, but I've got a million questions. But anybody else got any questions they want to ask Nick? Also, don't go too long because you haven't got that much.
That's quite often the case.
So everyone knows
Don't set him off again.
Ben.
So I was going to say the 1.68 things.
Yeah.
Could you just quickly describe that again?
Yeah, I'll do my best. Basically, it's like, you know, pi goes on forever as a number and it never repeats itself. Well, your Fibonacci is basically the same thing. It's 1.6180334, and it just goes on and on and on. And it's an important number because if you divide 8 into 13, you get 1.6180334. And if you divide 13 into 8, you get 0.6180334. Now, and what that gives you is called the golden mean, the perfect cut, the golden proportion. It's the same proportion as a Swan Vestas pack. The Swan Vestas pack will be 1.618 along one side from the other.
Credit cards are the same, yeah?
Credit cards, Georgian windows on Georgian houses.
Yeah.
Paper sizes.
Yeah, paper sizes.
I
some
bet
of them.
furniture.
The ones that look nice.
Yeah.
Furniture. And also loads of the classical paintings. And loads of Leonardo da Vinci's paintings. Although the content's quite attractive, they say that what's actually attracting you is the fact that his picture's laid out like this. That there's a given chunk of subject matter over here and over here that concentrates here. And that a lot of those classical painters did that. So it's a proportion that is just very pleasing to us. And of course it's not only the relation of all your bones and stuff, but where leaves turn out on a plant stem are going to be determined by the Fibonacci. And what it does is it maximises the amount of sunlight each leaf gets and minimises the amount of sunlight it robs from the other. That's the 1.618, 0.618 relationship. That's what it's doing. And the other thing about it, so it's a bit of bonus arithmetic, is that if you add, it's called phi, 1.618, the big one is called phi, and the little one, 0.618, is called phi. And if you add phi squared and phi cubed, you get phi to the power of 5, which means you're using addition to add cubic spaces. And that's how that's working, or a snail shell. It's not just working in 2D like that, like these are. What's happening is you start off with the little place where the tiny little thing that's going to be a snail lives, and what it does is it produces something that is a square of the thing that it's living in. So it's making more cubic space just by adding up, and you can only do that at the golden cut. You can't add one thing to another and get that kind of cubic progression in any other way than this one, which is why it's so common. There is actually another series of numbers that's like the Fibonacci but different. They're called Lucas numbers and they're much rarer. And actually, I've just thought of another thing I'd like to say, is that when I said these were like all the shapes, these 18 shapes, actually I wasn't quite telling the truth, because you remember how we managed to get an octahedron by putting dots in the centre of the cube and joining them together? Well, you can take any of these shapes at all, any of the next 13 shapes, and put dots in the centre of all the faces, join them together with beams of light on the inside, and what you get is a whole new 13 set called the Archimedean duals. These are called Archimedeans, and these are really worth looking at, because this one's the purple one, so it's grown out of the dodecahedron, and you can see that it's actually shaped like an icosahedron. So this has actually turned into, at its furthest projection, this is turning into its reflection. And the same thing applies to this one. If you remember this, the yellow ones grow out of the octahedron. They're reflections of a cube. And when you look at the furthest extension, oh look, it's been squashed, never mind. When you look at the feet, it's becoming like a cube. The octahedron becomes very much like a cube. The fixed is becoming the volatile, and the volatile the fixed, if you like. The one I really like though, and we might have to go right the way to the end for the last picture, which I don't think we've had yet, is that if you put points in the centre of each of these faces and join them together, what you end up is the only shape of the year I've ever had that was shape of the year for 2 years running is this one, which is the Archimedean dual of the cube octahedron, this one. So put a dot in the centre of each of these faces, join them together, you get this really amazing little thing that looks like 4 cubes stacked into the place of 3. So imagine my amazement when somebody gave me a rough garnet that is exactly one of these. It is. I've seen another one since, I've seen a shiny one, and it grows like that. The rough garnet, as well as doing the octahedron, does the Archimedean dual of the cube octahedron. These are really rare shapes, man. You know, you won't see these really. Look what happens to that one. That's this one. Really brilliant, and yet nature's managed to turn one out in the shape of a crystal. The only other thing I'd like to point out is that although we said that you don't see many of these feminine shapes because they've been hidden from us, this is the one feminine shape that you have seen a lot over time. Exactly right. There we go. If we colour it differently, it looks like that. Kicked around on a muddy field on a Saturday afternoon. By men. Yeah, indeed.
And women as well, to be fair.
I've got that bit. Yeah. Any more questions?
Any more questions?
Yes.
Why do you think the cube octahedron is more important than the icosahedron? You have emphasized that it's...
I don't really know. I tend to think it's more important because Buckminster Fuller thinks it is. It's possibly because it's been used in a lot of modern fibres and stuff. I don't think it is more important. It's kind of featured more heavily. You see it more often. But the cube octahedron's being used, they're kind of using like its feminine bonding qualities to make polycarbs that are really, really strong. So they're kind of, the cube octahedron, the reason why I emphasise the cube octahedron is because it's at the heart of these shapes. It's at the heart of the two star tetrahedra. You won't find the marriage of earth, of ether and water at the heart of any other shapes. I think because all of the reflections are different from each other. The reason why I follow the cube octahedron is largely because this was the end of all our pursuits, if you like, in terms of the geometry. We've got other outrageous pieces of hypergeometry that are really stunning, but they don't in any way emphasise any of these other shapes. This one is so much the kind of product of the 2D flower life, the flat thing we looked at, all lent together, and the fact that at the very heart of this is a cube octahedron. And there's no getting away from it. And so in here, if you look right at the heart of these four edges, basically that's a square that's made up of one unit in here. And then if we move out, there's one that's made up of 2 units. So it's still going to be a cube octahedron, it's just bigger. And this one, the one on the outside, okay, it's got a kind of a brass hoop around it, but it's got 3 units around its edges, but it's still a cube octahedron. And if you were to build the missing bits in, if you were to join those cube octahedra together, like's been kind of done in here, what you end up with is star tetrahedrons. So the cube octahedron and the star tetrahedron seem to me to be the 2 key shapes in 3D form. That's just because that's where we got to with them, really. And once you get beyond that, you start dealing with hypergeometries, which are, we've got like a tesseract, which is sort of 4 cubes on one side, 4 cubes on the other side, and they're kind of joined with spirals in the middle. But we've got a cube that's made up of 6 of those put together, and there's a shape in the middle of them which is like a really hyper star tetrahedron, and we've got one of those as well. But they're not the same geometries. They are close approximations, but because they're hyper, they have to have all sorts of distortions made to them to actually make them makeable. Right? But cube octahedron's emphasised because it's at the heart of this, really. And the flower life, Metatron's cube, in geometry terms, that drawing is all you need, which is why we've got lots of jewellery and stuff that's made of this stuff as well. And we found that one of the most effective things to wear is the flower life, i.e. the flat version of one of these, which looks like this. One of these round your neck. Absolutely, obviously not this big where you could.
Very clean. Yeah. Get them.
You can't get them in silver, get them in gold. And they do actually change. Like I say, the reason I got involved in all of this stuff is we found that your electromagnetic body is strengthened by looking at these geometries. Anybody done kinesiology in the room? Some, not many. It's basically a system where if you lean a little bit on somebody's arm, if they're saying no, if their internal navigator is saying no, it will just go weak. If their internal navigator is saying yes, it goes strong. And what we can do is we can actually get people to touch them in. The test point for the fire, for example, is in the perineum down here. Touch the perineum, just look at a wall, have somebody test you, you'll test weak. Touch your perineum, look at a tetrahedron, have somebody test you, you'll test strong. Similarly, strangely enough, they'll test strong if you look at fire, which is of course what Plato said the tetrahedron was associated with. Now, the reason I've started talking about that is because we stopped doing that work for 2 or 3 years because there's so much else going on. It's now become apparent that we wanted to start doing the ceremonies again, because what we do is, as well as showing that there's a connection between these things, there's then a ceremony which permanently reconnects the circuits, permanently strengthens your electromagnetic system so you no longer have to look at the tools. And we did it recently in Birmingham. There's several people here who experienced it, including one person who slept all the way through it. It worked really well even on him. And also somebody who claimed that he was deeply cynical about it and volunteered for the muscle testing. And the same thing happened as always happens. As soon as you test the first circuit, it goes stronger. They look at you and they go, how did you do that? It's a fantastic thing. We will be doing more of it. So it's worth keeping an eye out because that's a physical introduction.
We'll get you back down here again. And
Brilliant. That'd be great to come back. Thank you very much.
yeah.
So it's remained unchanged over time, and that's what I think is sacred. I think that's a good definition for sacred. It's also at the foundation of all natural design, at the heart of things. Another definition I found that I quite like is that which is found at the core. And your immune system, when it's not being screwed about with too much, is actually capable of dealing with invading systems that have never been seen on planet Earth before. And it can do that because all of those invading things will be geometrically based, and so are you. So your immune system can look at what's coming in and it can come up with a suitable countermeasure because the whole thing's geometric. So your actual natural system is built of all of this, foundation of natural design. Another thing that was pointed out to me is that most of the geometry can be done without any measurements, without a protractor, without any of that complicated nonsense you got taught in geometry at school. All you need is a pair of compasses and a straight edge. A ruler can be, but it doesn't need to have gradations on it. And I know there's several people in this room now that have started finding out what fun it is just playing with the compasses and the straight edge. All of the geometry that's coming up here has been done that way. None of it, we haven't cheated on any of it. The thing is, again, because it's at the foundation of your natural design, as soon as your body starts playing with it, even the most simple things, even this, 2 circles, one based on the edge of another, it's just doing that and looking at it. When you paint it on a piece of paper instead of looking at one that somebody else has done, it becomes fascinating. And very quickly you can get drawn into this stuff. There's lots of books out there now showing you how to do it. Although when I first was taught about this stuff, there were hardly any geometry books out there. There were no toys to play with. But we were told by our teachers that over time these things would become available. And I literally went from having no interest in geometry to being a complete geometry nut, more or less overnight, as a result of being exposed to this material. So it's all I've made it all nice and posh and put a lot of bells and whistles on it, but it's still fundamentally the stuff that turned me on. And of course the principles of this stuff have been used in all of our sacred sites. They're used in ancient barrows, they're used in stone circles, they're used in churches. Even the New World Order is quite clearly, absolutely obsessed with these particular forms. Washington DC is laid out on this design. It's a vesica piscis, it's got key items at various points on it, and they project into this a lot of the other geometries that we're going to be seeing. Now they don't go around building a whole new capital city that way for no good reason. And once again, the people that are using the geometry for those purposes understand entirely how resonantly important all of this stuff is. So, in order to, before we get down to the sort of actual geometry itself, we're going to work our way out of hyperspace, if you like, down towards the dots, which is where geometry starts. And as I kind of go backwards like that, gives me a bit of a chance to explain some ideas to you that are going to be helpful a little bit later on. And this is done by a chap called Mick the Moon. He's the man that runs my website for me. He's also my resident scientist who tells me when I'm bullshitting, so I try not to bullshit. He tells me this is a slice through a 7th dimensional hypercube. And Mick knows about these things. And already you can presumably see something that is not staying very flat on the screen. You should be seeing in there lots of little cubes are trying to jump at you. And also there should be spheres that look like they're made up of probably about 7 cubes, because it's 7-pointed symmetry in there. And the thing is that this is actually one of the first concepts we like to look at. As well as being a hyperdimensional thing that's just bending out at you, it's also absolutely flat. It's got a kind of length and a height to it, but it's made out of light just twinkling on that piece of sheet there. So it's got no thickness at all. It's a proper plane in the real sense of the word. The actual sense, the actual original design, can you turn on to the next picture for me? This is the thing from which that came. Mick had made that an arty thing, and he bent it and warped it and coloured it. But this is the original plate from which it comes. It's called a Penrose design. It's a kind of fractal shape because all it is 3 different shapes of diamond used to make a really complicated shape. We've got the diamond in the middle of the 7-pointed star here, and then the diamonds that surround that, and then the little thin diamond. And those 3 shapes are then used again and again to make this complicated design. This is the thing that I stole as my my logo, so wherever I am on the internet you see one of those but coloured in. Now most people will again be looking at spheres and cubes that are kind of not flat, they're kind of coming out of the screen at you. Everybody see that? And most people will be finding it hard to see symmetry in it. You can see symmetry in here, but the rest of it will be a bit wild to most of you, not all of you. And the thing is that if you look at this central point, see the 7-pointed star, then see these 7, then those, and let your eyes just move out in rings, out and out and out, you'll actually see that the symmetry goes all the way around. So there's 7 of these, and 7 of the next things out. And again, because we're all bipedal, we've got even numbers of things, we tend to look for even symmetry. And so once we see one of these hyperdimensional shapes, or something that's only got 7 or 9 in it, it really starts confusing our systems. Also, it's not something you come across very often because dividing 360 into 7 is really quite difficult. So straight away we've got a couple of planes, a couple of flat things that look really 3D. And all that's happening here is these things are kind of growing from self-similarity. We might say Spirit's got this idea for 3 shapes and then it's sorting out what it can do with them. I quite like the idea of making 3 concrete moulds that are like this and then trying to get a patio or a path that works like this. It'd be really grand to sit and have your pins on that, wouldn't it? So that's this image is a plane. It's 2D 3-element construction, but interacting with your cognition, it becomes something a whole lot more complex. It becomes a masterpiece of complexity. It's just basically a bunch of black lines on a flat surface. But not to us, it's not. Can I have the next picture? The next one's called a Koch snowflake. It's a simpler idea of the same thing. This is a closer thing to a fractal. What I did here was I've got several pieces of coloured card, and I kicked off with a big pink triangle in the middle. And then I made some green triangles whose sides were half the length of the pink triangle, and some orange ones that were in half the size of the green. And the result of that is we can fit 4 of the green triangles into the pink. We can put that one in there. So when you look at some of these shapes, you're stronger than when you don't look at them. So your system is already familiar with all of this stuff. And as I hold some of the shapes up, not all of them are here, I've got more that I'll use in the second half. Some of them are going to sing to you more than others. And that's because inside you, inside the resonant library of your DNA, there are counter codes for these geometric shapes. Your body, your biological system is reaching out to these things and singing to them. They're basically like frequencies of frozen light made out of brass and paper. These ones I made myself. I started off with white bits of paper and I made the forms on the computer and coloured them in and then made these shapes out of them. All the metal ones that I'm going to use are made in Bali. We tried to get them made all over the world. And it turned out that the people who did commission them, they live in Bali or spend a lot of their time there. And they finally found, having gone round trying to find people in America and people here, the people who were going to build it were living in a rice paddy just on the other side of the town from where they lived. So I made the cardboard ones, the other ones are made in Bali. Sacred geometry, what is it? The word geometry is easy. The word geometry is really the way number unfolds into space. We're going to be looking at how that happens visually today, but also you can hear it. Music is geometry for the ears. All music is to do with vibration, and so is all form. So the geometry bit of it is the way number unfolds into space, either as sound or resonance, or as visible artifacts, or indeed as vastly complex living systems, where tons of simple geometry is simply stacked up on top of itself. The real problem I had with defining the name of the talk was what is meant by the word sacred. It's actually a difficult word because it's defined really differently in different places. In the end, though, I thought that one of the best meanings for sacred is effectively that which remains unchanged over time. You know, most of the information that we get changes a lot. So our science, like, if you like, our science is changes regularly. It's constantly updated. Science tells us that given things are true right now, and then it changes its mind tomorrow when it finds something else. And these aren't small errors, you know. Sometimes it's like, in Shakespeare's time, Rosalind said, "This earth of ours is but 6,000 years old," because that's what they believed then. They thought the earth was created 4004 BC. There's still, unfortunately, a substantial part of the population that believes that now. Of course, science is suggesting that the earth's actually 4,500 million years old now, which is a bit different from 6,000 years, no matter how much you cook it up. The thing about this information is that it's older than our oldest texts. So even our Bible, even our holy texts, they get updated all the time. So if you look at the Old Testament, you'll see that it's a kind of mixing of several different versions. It's constantly being edited and updated. So you'll see Joseph being thrown down the well once, but he's rescued twice because somebody doesn't manage to remove some of the older stuff that they don't want in there. Now this information hasn't changed. This stuff was first written down 350 years or so before Christ by a Greek called Euclid. And although we've learned lots and lots more about the geometry, we've learned loads more about its applicability, about where we're likely to find it. The actual basic data that I'm giving you today is older than our oldest text. This one in here, that one in there, and there'd be room for another green triangle in the middle. So we can fit 4 green triangles in the pink, 4 orange into the green, 4 yellow into the orange. They're really fascinating this close up. They're all pulsing and checky. And pink into the yellow. Now, this already is a really beautiful looking thing, but you can see how just the simplest of plane shapes, just a triangle, by reflecting on itself, is already getting the idea of growth and pattern and beauty. You can see movement in this thing. This one thankfully does look just flat. Now, one of the important things about this particular shape, you can't quite see it properly because the top part of it is missing. If you put a triangle round this shape, you could keep adding more of these things. If I had an infinitely sharp pair of scissors, I could keep adding smaller and smaller triangles to this, and they'd never step outside the original triangle that it's sitting in. And we can see that because I started with a pink triangle, and then I did the green ones, then I did the orange, then I did the yellow, and then I did the little pink. And if you look, the tip of this orange is in line with the tip of that pink, and the tip of this pink's in line with the tip of the orange. So effectively, we could continue to cut smaller and smaller triangles and stick them on the outside of this. Its surface area would be growing forever, effectively, without it ever going outside the boundaries within which it grows. Now, here in the third dimension, we've got this impression that stuff can only grow at the expense of something else. Actually, in the hyperdimensions where we naturally reside, that's not the case. Everything exists where everything else already is. If you were to look at us from the dimension in which we actually exist, all of our hearts, for example, put out electrical signals that reach tens of feet away from the body. Effectively, all of our electrical heart signatures, if you like, are interwoven here. If you were to look at that particular image of this room, you wouldn't be able to see thousands of individuals. All you'd see is this huge pulsing ball of our heart energies responding to each other. So, this geometric idea that you can grow without stepping on the feet of other things is important, because you can do that. The other thing about this, we have the next picture, is that if we use the same triangles, we can get it to grow inwards as well. You can put a green triangle in the middle of the pink and then an orange in the middle of the green, and one way and the other, it can grow inwards as well. You could keep carrying, if you had the infinitely sharp pair of scissors, you could keep cutting smaller and smaller triangles from the middle. That's basically a simple fractal form. It is simply taking the original shape and taking something half the size but the same shape, and then from that growing a complicated pattern. It's not had to do very much work at all. Now, these ideas, this idea of kind of constantly changing a shape, was first developed by a guy called, or maths was first developed by a guy called Leibniz a couple of hundred years ago. We have the next picture. And the result of that was these modern fractals. Now, these were in Leibniz's head 200 years ago. he kind of knew we'd be able to do this. But it wasn't until we developed computers that we had something that could do the thousands of millions of calculations necessary to produce an image like this. Now effectively, there's lots and lots of different fractal designs like this, and all they are is a really simple. Thank you very much. Evening everybody. Welcome to this introduction to sacred geometry. It's subtitled From the Dot to Hyperspace, no previous experience necessary, and that's genuinely what we'll do over the next, like you say, it takes about an hour and a half, probably will be about an hour the first bit. It's always a bit random, can never tell quite how it's going to distribute itself. But you should get a fairly thorough introduction to the subject from this. The first half of it, I'm hoping I'm going to introduce these 5 basic shapes to you. They're called the Platonic forms, and those are the kind of aim, if you like, for the halfway point. In the second half, we're going to be talking about hypergeometry and various other shapes that are grown from the shapes we're going to learn about in the first half. It's a talk I've been doing for now 3 or 4 years, this one, but recently it's been sort of revamped and re-illustrated. We've got a load of models here that aren't very often seen, and some of the models I normally carry around I haven't got with me, so it's going to be a bit of a new thing, and I'm going to have to try and keep track of my notes, otherwise I'll miss out some of the important stuff. It's a great story. There's a bit of a density warning on this one. We're effectively going to do what's basically a whole term's work in about an hour and a half. You can just be thankful that they're going to give you a bit of a break in the middle, because some people do get to sit through the whole thing in 90 minutes, and it's but so even in doing it this way, you'll have a tendency, because there's a lot of stuff, maybe to want to wander off a bit, close your eyes and stuff. You don't need my permission for that. All of the information will go in anyway, even if you are nodding slightly. I know there's a couple of people here who will verify that that's the case. So the reason why we're interested in sacred geometry is because it's not just a matter of form. It's not just a matter of simple shapes. It's because it's the form of the world in which we live. Effectively, you can almost see the shape of the sub-ether in some of the shapes that we're looking at. Most importantly of all, the simple rules that we're going to look at today about growth and reflection and other things mean that right down to the tiniest scale and right up to the biggest scale, these are the geometries that count. So each of us is made up of billions of centres of vibrating energy. We now know that what we're calling particles are actually just little balls of energy. They're not hard at all, they're mostly space, and we're made up of billions of balls of energy, functioning in a field that's made up of other lines and centres of force. So we and everything about us are made up of these little centres of energy. And the distribution of this energy is governed by the same geometries that define the cosmos. From the tiniest quantum event through all of biology to galaxies and the hearts of stars. The principles and forms examined in this presentation underlie absolutely everything. So it really doesn't matter what scale you're going to look at. You're going to see the kind of things we're going to show you today. There's not going to be any sums, there's only going to be images and models. That's not quite true, there's some tiny sums about halfway through, but they're totally non-threatening sums, and mostly it's to do with the shapes. The other thing that's important is that your biological system is already attuned to all of the shapes that I'm going to show you. This is another thing that I do occasionally, is we do a sort of ceremonial introduction to geometry, which actually wires these shapes into your electromagnetic system. And we can show using kinesiology that this is the case.